Image of binary code in green on blue background. Figure 8. One big data taxonomy includes data providers, data consumers, data owners, and data viewers while providing the data flow between them. Credit. Modification of DARPA Big Data by Defense Advanced Research Projects Agency, DARPA/Wikimedia Commons, public domain. Chapter Outline. 8.1 Data Management Focus. 8.2 Data Management Systems. 8.3 Relational Database Management Systems. 8.4 Non-Relational Database Management Systems. 8.5 Data Warehousing, Data Lakes, and Business Intelligence. 8.6 Data Management for Shallow and Deep Learning Applications. 8.7 Informatics and Data Management. Managing data today requires an end-to-end perspective and the ability to combine the use of various types of data. For example, Amazon needs to run its day-to-day businesses and sell products to customers, handle returns, pay commissions to retailers and wholesalers, and develop and price new products. This is all part of day-to-day operations, and most retail companies strive to achieve operational excellence as it is a key driver of customer satisfaction. For that purpose, retailers typically use traditional relational databases and structured data to run their operations. At the same time, retailers need to remain competitive and develop with pricing strategies that attract and retain customers. Doing so requires being able to analyze market prices accordingly before advertising products to their customers. For that part, businesses generally rely on datasets and big data analytics to predict competitive prices in order to optimize sales. Overall, businesses and organizations that deliver products to customers need to leverage insights coming from metadata to transform as they perform and remain competitive while sustaining their operations. It is no longer possible to rely on operational excellence to ensure continued success. In this chapter, we will cover the spectrum of data management activities, including the storage and retrieval of various types of data. In other words, the chapter is about how big data are managed today from an end-to-end standpoint. As an example, TechWorks is a startup company that is 100% committed to leveraging innovative technologies as part of its repeatable business model and as a business growth facilitator. TechWorks has multiple departments including human resources, finance, sales, marketing, operation management, and information technology. Each department has its own information system and database. They do not share any resources. TechWorks has many success stories in the market. However, they have a huge problem with integrating their reports to aid in decision-making. TechWorks has many challenges that impact their competitiveness and survival in the market, including their traditional database not working properly, their practices in collecting, managing, and analyzing data not promoting better business decision-making, and their servers being old and sometimes unable to sufficiently handle the company data. The Chief Executive Officer, CEO, of TechWorks decides to develop a new database management system with the following objectives. Integrate all of the department's practices into one system. Use the cloud to store, manage, analyze, and maintain the data. Hire a data scientist, computer scientist, and information architect to work as a team with the database designer and the database administrator. Apply the extraction, transformation, and loading process to the data. Use business intelligence and machine learning tools to make decisions based on the data. Learning objectives. By the end of this section, you will be able to discuss data management and its relation to computer science and data science. Understand that data are the backbone of the industry. Identify and explain key concepts in data management. Distinguish various roles in the field of data management. Explain the current state of data management. In the current digital world, collecting information and facts that are stored digitally by a computer or data is a straightforward process. There are many direct and indirect ways, such as social media, that support the data collection process. A large amount of data is collected every day, every hour, and every minute. But this amount of data is not useful unless benefits can be drawn from it, which requires knowing what to do with these data. In this context, data are like the crude oil that needs to be stored digitally in order to allow extraction of information and knowledge via information and knowledge management systems. Related structured data is stored in a database management system. The knowledge supports the decision makers in any organization in making important decisions, such as increasing the sales in some regions, changing the suppliers within the supply chain, decreasing the manufacture of a specific product, modifying the hiring process, studying the community culture, and identifying customer demand. It is clear that proper data management is required to support decision makers. The study of managing data effectively, or data management, treats data as a corporate asset similar to physical assets such as plants and equipment. Data management requires having a strategy to analyze the data by collecting data, then storing the data, cleaning the data, preprocessing the data, and preparing the data for analytics, which will lead to decision-making. Concepts in practice. Managing your social media data. Facebook, Instagram, LinkedIn, Snapchat, TikTok, X, and many other social media applications are controlling your data. You are most likely posting too much information about your life, work, and school, but it is not only you. Everyone is sharing data on social media. A supermassive mother of all breaches, Moab, publicized discovered in early 2024, contains data from numerous previous breaches, comprising 12 TB of information from LinkedIn, X, formerly Twitter, Weibo, Tencent, and other platforms, user data. Have you ever asked yourself how service providers are managing this data? How do they store the data? Where do they store it? Which database are they using? And the big question: can we benefit from this data and manage our own data? Meta is offering the option to control your Facebook experience by managing your data. All you need to do is complete a form, which gives you multiple options such as downloading your data, managing ad preferences, and removing a tag from a post. 1. Data management in computer and data science. Computer science is the study of computing algorithms that receive data as inputs, process data, and produce outputs. Computer science applies the principles of mathematics, physics, and engineering. Hardware, software, operating systems, and applications are working together to perform computer science computations. Data science is the study of extracting knowledge from information using hypothesis analysis and algorithms. Information is the result of processing raw data. Figure 8. 2 illustrates the skills and knowledge needed to be successful in data science. Circles with computer science, mathematics and statistics, and business domain knowledge overlap, creating machine learning, data science, software design, and data analytics. Figure 8. 2 Data science combines programming skills, analytic systems, statistics, and data mining. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Data management in the industry. Data are the backbone of any enterprise because analyzing data improves performance and increases profit. Gathering raw data from various sources and processing it for modeling is about 80% of the data scientist's work. 2 enterprise projects usually involve a massive amount of data, which makes it impossible to be stored locally, so many businesses move their data to the cloud. A business may also choose to run applications, as well as databases and operating systems in the cloud. Data management is often handled by a separate data engineering team because most computer and data scientists do not have enough knowledge about data storage and infrastructure. Industry spotlight. Industry data management. Data management is important in every industry today. The main benefit of data management is to minimize potential errors by controlling access to data using a set of policies. Elaborate on how useful it is to know about data management in retail industries for product marketing purposes. Hint: data management can help with targeted advertising, for example. Data management aspects. There are various aspects of effective data management: metadata cataloging, metadata modeling, data quality, data accuracy, data completeness, and data consistency, and data governance, which we will discuss in more detail in the following subsections. Metadata cataloging. Metadata are used in a database management system, DBMS, which is a system that creates, stores, and manages a set of databases. In a DBMS approach, metadata are stored in a catalog called a data dictionary. A data dictionary is a set of information describing the content, format, and structure of a database, e.g. In a relational DBMS, the catalog includes the names of all available tables and their associated fields. The metadata catalog constitutes the heart of the database system and can be part of a DBMS or a standalone component. The metadata cataloging process is collecting data about processes, people, products, and any enterprise-related data, which provides an important source of information for end users, application developers, as well as the DBMS itself. The catalog typically provides an extensible metadata model, import-export facilities, support for maintenance and reuse of metadata, monitoring of integrity rules, facilities for user access, and statistics about the data and its usage for the database administrator and query optimizer. Metadata cataloging improves the user experience, adds competitive advantages, and improves the efficiency of the business. Metadata modeling. A business presentation of metadata is metadata modeling. A database design process can be used to design a conceptual model of a database storing metadata as an enhanced entity, relationship, EER model, Figure 8.3, or Unified Modeling Language, UML model. EER and UML are used to create models for designing large systems. Metadata modeling may cover various views of these models. For example, EER models and UML class diagrams help express views of a data model. While EER focuses purely on data modeling, the UML notation may be used to express comprehensive models of information systems using additional diagrams. Box with artist leading to circles with ANR and a name. Artist linked to singer and actor with lines, bisected by arcs. Singer box linked to music style, Figure 8. 3. This EER diagram models a product entity and states that a product can be either shipped or picked up but not both. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0. License. Data quality. The measure of how well the data represents its purpose or fitness for use is called data quality, DQ. Data of acceptable quality in one decision context may be perceived to be of poor quality in another. Data quality determines the intrinsic value of the data to the business. Businesses may use the concept garbage in, garbage out, GIGO, which means that the quality of output is determined by the quality of the input. Poor DQ impacts organizations in many ways and at different management levels. For example, it negatively impacts operations in day-to-day operations. However, it makes a big difference at the strategic level in making decisions. DQ is a multidimensional concept in which each dimension represents a single aspect such as views, criteria, or measurements. DQ comprises both objective and subjective perspectives and can categorize different dimensions of data quality. The DQ framework has 4 categories: intrinsic DQ, contextual DQ, representation DQ, and access DQ, as illustrated in Figure 8. 4 Data Quality Framework Hierarchy Chart, second level. Intrinsic DQ, contextual DQ, representation DQ, access DQ. Third level, data accuracy, data completeness, data consistency, data, Figure 8. The 4 data quality framework categories are intrinsic DQ, contextual DQ, representation DQ, and access DQ. Attribution, Copyright Rice University, OpenStax, under CC by 4. 0. License. In the intrinsic DQ category, data accuracy refers to whether the data values stored for an object are the correct values, and they are often correlated with other DQ dimensions. We can count the data reliability as a part of data accuracy. The degree to which all data in a specific dataset are available with a minimum percentage of missing data is called data completeness. It can be viewed from at least 3 perspectives. Schema completeness, the degree to which entity types and attribute types are missing from the schema. Column completeness, the degree to which there exist missing values in a column of a table. And population completeness, the degree to which the necessary members of a population are present or not. The data consistency dimension is part of the representation category and can also be viewed from several perspectives. Consistency of redundant or duplicated data in one table or multiple tables, consistency between 2 related data elements, and consistency of format for the same data element used in different tables. The accessibility dimension is part of the access category and reflects the ease of retrieving the data from the underlying data sources. This often involves a trade-off with security, which is also part of the access category. There are many common causes of bad data quality, such as the following: computer processing, duplication, multiple data sources providing the same data, which may produce duplicates, consistency problem, different occurrences of data or incorrect data, objectivity problem, data giving different results in every process, limited computing resources, insufficient computing resources limiting the accessibility of relevant data, accessibility problem, large volumes of stored data making it difficult to access needed information in a reasonable time, human intervention, biased information using human judgment in data production, relevance problem, different processes updating the same data, data quality problems, decoupling of data producers and consumers, data governance and compliance. The set of clear roles, policies, and responsibilities that enables a business to manage and safeguard data quality using internally set rules and policies is called data governance. The related concept that ensures that data practices align with external legal requirements and industry standards is called data compliance. For example, the UK GDPR, General Data Protection Regulation, is the United Kingdom's data security regulation, modeled after the EU GDPR that governs and regulates how UK organizations and businesses collect, store, use, and process personal data. Using data governance, data are managed as an asset rather than a liability. Data governance has three dimensions: technology, people, and process. It should include standard roles for quality, security, and ownership. In planning for data governance, we should answer four questions: what, how, why, and who. What policies should we include? How do we integrate the policies with the enterprise business process? Why do we need this policy? Who will be part of this policy? Different frameworks have been introduced for data quality management and data quality improvement. Total Data Quality Management, TDQM, Total Quality Management, TQM, Capability Maturity Model Integration, CMMI, ISO 9000, Control Objectives for Information and Related Technology, COBIT, Data Management Body of Knowledge, DMBOK, Information Technology Infrastructure Library, ITIL, and Six Sigma. These frameworks provide guidelines for organizations that define how a product or process should be based on high-quality standards. The main issue in these frameworks is that they may cause failure when the system is not considering all of the processes in a correct flow. It is possible to annotate the data with data quality metadata as a short-term solution. Unfortunately, many data governance efforts, if any, are mostly reactive and ad hoc. Global issues in technology. Chegg is an educational technology company based in California. It offers various online services such as textbook rentals, tutoring, homework assistance, and more to students around the country. In April 2018, an unauthorized party gained access to Chegg's database. This database hosted user information for both Chegg and its affiliated companies, e.g., EasyBib. The hacked information included names, emails, passwords, and addresses, but did not include any financial information or social security numbers. After discovering the breach, Chegg implemented plans to notify the 40 million affected users. The motivation for the attack is still unclear, but it is likely that a third party sought information to profit from identity theft. What are some things that Chegg users can do to protect themselves from this hack and future breaches of personal information? Data management roles. Within any organization, there are various data management roles including information architect, database designer, data owner, data steward, database administrator, computer scientist, and data scientist. Their roles are outlined in the following sections. Information architect. An information architect, also known as a data architect or information analyst, is responsible for designing the conceptual data model, blueprints, to bridge the gap between the business processes and the IT environment. The information architect collaborates with the database designer, who may assist in choosing the type of conceptual data model, e.g., EER or UML, and the database modeling tool. Figure 8. 5 shows an example of different database systems that various personnel working in data management may encounter. Illustration of different database systems that various personnel working in data management may encounter. Figure 8. 5 existing database systems can be categorized as non-relational and relational. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0 license. Database designer. A database designer is responsible for creating, implementing, and maintaining the database management system. Other responsibilities include translating the conceptual data model into a logical and internal data model, assisting the application developers in defining the views of the external data model, and defining company-wide uniform naming conventions when creating the various data models. Data owner. The data owner has the authority to ultimately decide on the access to and usage of the data. The data owner could be the original producer of the data, or the data could originate from a third party. A person who assumes the role of a data owner should be able to insert, edit, delete, or update data, as well as check or populate the value of a field. The data owner is the one responsible for checking the quality of one or more datasets. Data steward. A data steward is a DQ expert who ensures that the enterprise's actual business data and the metadata are accurate, accessible, secure, and safe. The data steward performs extensive and regular data quality checks, initiates corrective measures or deeper investigation into root causes of data quality issues, and helps design preventive measures, e.g., modifications to operational information systems, integrity rules. Database administrator. The database administrator, DBA, is responsible for the implementation and monitoring of the database, as well as ensuring databases run efficiently by collaboration with network and system managers. Computer scientist. A computer scientist is a person who has theoretical and practical knowledge of computer science. The computer scientist will solve problems using technology by applying computer science practices. Computer scientists typically focus on building end-to-end solutions for companies. For example, computer scientists can create software applications that implement complex algorithms and store and retrieve related data into and from database systems. Computer scientists may also be involved in designing and fine-tuning complex machine learning algorithms. Data scientist. Data scientists typically focus on creating classification and prediction models by training existing machine learning algorithms. The resulting trained models act as programs to help classify new data or predict an outcome based on input data. In general, a data scientist is a person who has theoretical and practical knowledge of managing data. A data scientist's background combines computer science, mathematics, and statistics. A person in this role is responsible for gathering a large amount of structured, semi-structured, and unstructured data to pre-process and prepare data for advanced data analysis to develop a product or to make a business decision. Data management roadmap. The data management roadmap has multiple steps, starting from collecting and storing data to having a final product or decision. Available databases vary in type and vendor, e.g., SQL, Hadoop, Spark, and MongoDB. Storing the data in databases is not hard, but the entire data management process most often takes place on the cloud, which adds a new set of necessary skills for the computer scientist and the data scientist. Massive data growth transformed the way data are stored and analyzed, and many applications and databases are hosted on servers in data centers elsewhere. While preparing data, data scientists and computer scientists should clean and format the data information to be used for the correct marketing use. We will discuss database types in more detail together with their data structure implementations, refer to 8.2 Data Management Systems, Technology in Everyday Life. End-to-end data management. End-to-end data management covers the data lifecycle within the system. A data lifecycle is a process that helps the organization to manage the flow of data, and it includes creating the data, storing the data, and sharing the data. A global positioning system, GPS, is an embedded system that mainly uses data to provide routes and destinations. Most of us use a GPS to check on road construction, traffic, or to find the shortest route. How does knowledge of end-to-end data management help people in their everyday life? Look at these data collections from all aspects of data management, including collecting, storing, and analyzing these data. Provide a few illustrative scenarios to explain your opinion. Footnotes. 1 Reg Bins, The Privacy Mindset of the EU versus the US, Forbes, updated April 14, 2022, https://www.forbes.com/site/forbes.council/2020/07/29/the privacy mindset of the UVSDA/ sh equals 215 A8 A127 D01. 2 Project Pro, Why Data Preparation is an Important Part of Data Science, updated April 11, 2024. https://www.projectpro.io article Why Data Preparation is an Important Part of Data Science 242. Learning objectives. By the end of this section, you will be able to define important terms and characteristics of data management systems. Explain the various aspects that characterize database management systems. Remember that data are any raw facts you can collect, such as the number 48,502. When we process the data, we have information that has meaning. For example, the number 48,502 is a zip code. When we have a collection of related data, we call it a database. To store, retrieve, edit, and maintain the related data in the database, we need a system called a Database Management System, DBMS. Definition and characteristics. Data, data model, database, and DBMS concepts are connected to each other. Data relate to known facts that can be recorded and have an implicit meaning. A data model is an abstract model that contains a set of concepts to describe the structure of a database, the operations for manipulating these structures, and certain constraints that the database should obey. A database is a collection of related data items within a specific business process or problem setting. An example of a large commercial database is the one maintained by Amazon.com. A DBMS is the software package used to define, create, use, and maintain a database while considering appropriate security measures. A mini-world or universe of discourse (UD) represents some aspect of the real-world data that are stored in a database, e.g., student grades at a university. There are many characteristics of the database approach, such as being superior to the file approach in terms of efficiency, consistency, and maintenance. Providing loose coupling between applications and data, as well as facilities for data querying and retrieval, removing redundancy and cleansing the data, supporting multi-user transactions that allow multiple users to access the same data and multiple views of the data, and allowing sharing data between users and applications. Think it through. University mini-world. Let us think about the university as a mini-world. In this mini-world, we need to define a data dictionary to describe the following: students, courses, sections, departments, and instructors. Suggest a mini-world that would be part of a university environment. Define the main entries to be included, such as students equals ID plus first name plus last name. Applications of database technology. A database application is a program or piece of software designed to collect, store, access, retrieve, and manage information efficiently and securely. The following are some examples of database applications: multimedia applications, e.g., YouTube, Spotify; biometric applications, e.g., fingerprints, retina scans; wearable applications, e.g., Fitbit, Apple Watch; geographic information systems, GIS applications, e.g., Google Maps; sensor applications, e.g., nuclear power reactor; big data applications, e.g., Walmart; and IoT applications, e.g., telematics. Concepts in practice. Specialized database systems. Database systems are fascinating because they must be given the ability to model various types of data at various levels of abstractions and various levels of details. Therefore, it is possible to create specialized systems that can help people in various research domains and industries represent and use their data in the best possible way. For example, SciDB is an open-source data management system intended primarily for use in application areas that involve very large-scale array data. SciDB can be used to support a large variety of scientific applications used in astronomy, remote sensing and climate modeling, bioscience information management, risk management systems for financial applications, and weblog data analysis. Elements of database systems. The major elements of a database management system include hardware, software, data, procedures, language, and users. Hardware includes the physical devices such as computers and hard disks. Software refers to the set of programs that are used to manage and control a database. Data includes raw data and information organized and processed within the database. Procedures are instructions used to manage the database. A database user is a person who has the privileges to access, analyze, update, and maintain the data, e.g., information architect, database designer, database administrator, database application developer, and business user. A database language is used to write instructions to access and update data in the database. Table 8. One shows different examples of database languages along with definitions and examples. Language definition: relational DBMS, SQL. Database description language, DDL, used to create, update, and delete storage structures in a database management system. Create table. Table name: column 1 data type, column 2 data type, column 3 data type. Data manipulation language, DML, used to create, update, and delete data in a database management system. Update table name. Set column 1 equals value 1, column 2 equals value 2, column 3 equals value 3. Where condition. Data query language, DQL, used to query the database. Select expressions. From table name. Where conditions. Data control language, DCL, used to control the use of features that are available in the database management system. Grant privilege. On object to user. Table 8. 1 database languages. Database systems and database management. There are many advantages to using a DBMS, such as controlling redundancy in data storage. When the same piece of data is held in two separate places in the database, data redundancy can occur. DBMS improves development and maintenance efforts, sharing of data among multiple users, and restricting unauthorized access to data. For example, only the DBA staff uses privileged commands and facilities providing persistent storage for program objects, e.g., object-oriented DBMSs make program objects persistent, providing storage structures, e.g., indexes for efficient query processing. Additionally, a DBMS provides data independence, which helps the user to easily make changes to the database. There are two types of data independence. The first, physical data independence, separates the conceptual level from the physical level, e.g., using a new storage device such as a hard drive. The second, logical data independence, separates any changes in the data from the data format. DBMS provides integrity rules by adding a primary key to guarantee that every record is unique. DBMS allows you to manage structured, semi-structured, and unstructured data. Data that have been organized into a formatted database and have relational keys, e.g., relational data, are called structured data. Data that are not organized in a formatted database but have some organized properties, e.g., XML data, are called semi-structured data. Data that are not organized in a formatted database and do not have organized properties, e.g., PDF, are called unstructured data. The DBMS provides a backup copy of the entire database, which is backed up as decided, perhaps once a day. The backup copy should be stored in a secured location and is used to restore the database in the event of failure, loss, or damage to the original data. Technology in everyday life. Databases impact all industries. Databases, database technology, and big data, complex datasets, have a tremendous impact in industries such as banking, insurance, retail, healthcare, real estate, e-commerce, law, education, and more recently, social networks. Data collection is also impacting advancements in the fields of medicine, environmental studies, science, and mobile technology. Can you think of any other industries in which the use of big data is surprising? Does big data benefit the users or the collectors? Will big data enable more scientific research and/or discoveries? Why or why not? DBMS facets. DBMS includes various components, as in Figure 8.6. DBMS interface is the main line of communication between the database and the user. There are many types of interfaces such as web-based, standalone query language, command line, forms-based, graphical user interface, GUI, natural language, admin, and network. DBMS component chart, DDL, queries, applications, database, double-arrowed to DBMS interfaces. DBMS consists of DBMS, query processor, storage manager. Disk storage and database files and data dictionary at bottom. Figure 8.6 DBMS includes multiple components: DBMS interface, query processor, storage manager, connection manager, security manager, DDL compiler, and database utilities. Attribution, copyright Rice University, OpenStax, under CC BY 4.0 license. A connection manager manages reports, books, objects, and batches. For each database, the connection manager provides the connection name, data source type, and value. A security manager is a collection of processes used to secure the database from threats. The data description language, DDL, compiler translates statements in a high-level language into low-level instructions that the query evaluation engine understands. A query processor acts as an intermediary between users and the DBMS data engine to communicate query requests including DML compiler, query parser, query rewriter, query optimizer, and query executor. A storage manager is a program that is responsible for editing, storing, updating, deleting, and retrieving data in the database, such as transaction manager, buffer manager, lock manager, and recovery manager. DBMS utilities are a set of utilities for managing and controlling database activities, such as loading utility, reorganization utility, performance monitoring utilities, user management utilities, and backup and recovery utility. Figure 8.7 illustrates the navigation window, results window, log window, and query window. Screenshot illustrating a navigation window, results window, log window, and query window. Figure 8.7. This sample MySQL Workbench graphical user interface shows the navigation window, query window, and result window. Credit, used with permission from Oracle. Data model categories. Data models can be conceptual, represented using EER or UML notations, logical, physical, or self-describing. The various logical data models can be categorized as follows. A hierarchical DBMS is a data model in which the data are organized into a tree-like model. DML is procedural and record-oriented. The query processor is logical, and internal data models are intertwined. GIMS from IBM. A network DBMS is a data model in which the data are organized into a network model. DML is procedural and record-oriented. The query processor is logical, and internal data models are intertwined. GCAIDMS from Computer Associates. A relational DBMS is a data model in which the data are organized into a relational data model. Use SQL as a declarative and set-oriented database. The query processor has a strict separation between the logical and internal data model. Relational DBMSs are the most popular in the industry, e.g., MySQL open source database from Oracle, Oracle DBMS, DB2 from IBM, and Microsoft SQL. An object-oriented DBMS is a data model in which the data are organized into an OO data model, avoiding impedance mismatch when used with an OO host language. It is also called OODBMS or ODB. GDB40 open source database from Versant, Cache from InterSystems, Gemstone S from Gemtalk Systems, which are only successful in niche markets due to their complexity. An XML DBMS is a data model in which the data are using the XML data model to store data. XML could be native XML DBMS, e.g. BaseX and exist, which map the tree structure of an XML document to a physical storage structure, or XML-enabled DBMS, e.g., Oracle and IBM DB2, are existing DBMS that are extended with facilities to store XML data. A not-only SQL DBMS, or NoSQL DBMS, comes in a variety of big unstructured data classified as a document, a graph, key-value stores, and column-oriented databases. NoSQL DBMS focuses on scalability and the ability to cope with irregular or highly volatile data structures, e.g., Apache Hadoop, MongoDB, Neo4j. The irregular data structures appear when the data don't follow a specific order or nature. The volatile data are usually stored in cache memory and is easy to lose. Single versus multi-user DBMSs. With a single-user DBMS, only one user at a time can use the database. A multi-user DBMS allows many users to use the database concurrently. A multi-user DBMS is illustrated in Figure 8.8 illustration of multiple laptops connected to server, with incoming arrow leading to dispatcher, leading to server instance 1, 2, and 3, connecting back at database. Figure 8.8 multiple users are accessing the same system at the same time in this multi-user DBMS. Attribution, copyright Rice University, OpenStax, under CC by 4. 0 license. DBMS users. DBMS users may be divided into actors on the scene who use and control the database content, design, develop, and maintain database applications, such as database administrators and database designers, and workers behind the scenes who design and develop the DBMS software and related tools, as well as the computer systems operators, including system designers and developers. DBMS architectures. There are various types of database architectures as follows: centralized DBMS architecture, n-tier DBMS architecture, cloud DBMS architecture, federated DBMS, and in-memory DBMS. In centralized DBMS architecture, the data are maintained on a centralized server at a single location, while client-server DBMS architecture has one or more client computers connected to a central server over a network. Active clients request services from passive servers. An n-tier DBMS architecture usually divides an application into 3 tiers layers: the presentation tier, the logic tier, and the data tier, e.g. a client with GUI functionality, an application server with applications, a database server with a DBMS and a database, and a web server for web-based access. In cloud DBMS architecture, the DBMS and database are hosted by a third-party cloud provider, e.g., Apache Cassandra Project and Google's Bigtable. A federated DBMS provides a uniform interface to multiple underlying data sources, which hide the underlying storage details to facilitate data access. An in-memory DBMS stores all data in internal memory instead of slower external storage, e.g., disk, often used for real-time purposes such as HANA from SAP. DBMS usage areas. DBMS applications include the following: online transaction processing, online analytical processing, big data and analytics, multimedia DBMS, and open source DBMS. In online transaction processing, OLTP, the focus is on managing operational or transactional data. The database server must be able to process lots of simple transactions per unit of time. A DBMS must have good support for processing a high volume of short and simple queries, e.g., RDBMS. In online analytical processing, OLAP, the focus is on using operational data for tactical or strategical decision-making. A limited number of users formulate complex queries to analyze the data. Therefore, the DBMS should support efficient processing of complex queries, which often come in smaller volumes, e.g., data warehouses. For example, complex SQL queries involve using queries beyond just the select and where commands. OLAP uses cube as a data structure that represents multiple dimensions to help in data analysis. In big data and analytics, the focus is on more flexible or even schemaless database structure, storing unstructured information such as emails, text documents, X, formerly Twitter posts, Facebook posts, e.g. NoSQL databases. A multimedia DBMS provides storage of multimedia data such as text, images, audio, video, and 3D games. It should also provide content-based query facilities. An open-source DBMS is publicly available and can be extended by anyone, e.g., MySQL from Oracle. Learning objectives. By the end of this section, you will be able to discuss the relational model, describe the theoretical and practical aspects of the structured query language, SQL, explain how to create a logical relational database design, demonstrate how to create a physical relational database design, discuss application programming interfaces and techniques used to program relational database applications. Identify the various components of a relational database management system. A relational database management system, RDBMS, is one type of DBMS that stores related data elements in a row-based table structure. An RDBMS transaction is a single logical unit of work that accesses and possibly modifies the contents of a database using read-and-write operations. Multiple SQL commands may be performed as part of a single RDBMS transaction as a single logical unit of work. For example, a student may register for multiple courses using a university's registration system. To maintain consistency in a RDBMS, transactions satisfy properties known as atomicity, consistency, isolation, and durability, ACID. These properties are necessary for maintaining data consistency, integrity, and reliability while performing transactions via RDBMS. Atomicity ensures that multiple SQL commands that are part of the same transaction are executed atomically, i.e., as a unit. In the example mentioned earlier, once the registration transaction is complete, the student will be registered for all 3 courses. If that is not possible because one of the courses is full, the transaction will not complete successfully. Consistency ensures that only valid data are written in the database. In the student registration example, it simply means that the registration information stored in the database will be consistent with the registration transaction that was completed. Isolation guarantees that multiple users that access the RDBMS concurrently will not be affected by the transactions performed by others. In the course registration example, multiple students can register concurrently without any of them noticing any side effects that result from the RDBMS being accessed by multiple students concurrently. Finally, durability guarantees that once information has been stored in the database, it will stay there permanently. In the course registration example, if one student registers successfully, the registration information will not change unless they decide to go back and perform another drop-add transaction. While ACID transaction properties ensure that stored data are reliable and accurate, they also come at a cost. For example, guaranteeing full isolation in a RDBMS requires significant additional processing time. Due to the use of database logical schemas that constrain the row-based table structure and require each field to abide to specific type constraints, RDBMS are not good at storing unstructured or semi-structured data. The rigid schema also makes RDBMS more expensive to set up, maintain, and grow. RDBMS requires users to have specific use cases in advance, and any changes to the schema are usually difficult and time-consuming. In addition, traditional RDBMS were designed to run on a single computer node, which means their speed is significantly slower when processing large volumes of data. Sharding RDBMS is a partitioning method that splits the database into smaller components, which makes the management process faster, but using it while maintaining ACID compliance is challenging. Relational model. The relational model of data is based on the concept of a relation. A relation is a mathematical concept based on the ideas of sets. The model was first proposed by Dr. Edgar F. Codd of IBM Research in 1970. A relation typically contains a set of rows. The data elements in each row represent certain facts that correspond to a real-world entity or relationship. In the formal model, rows are called tuples. Each column has a column header that indicates the meaning of the data items in that column, and the column header is referred to as an attribute name or just as an attribute. Multiple attributes may be selected to form superkeys that uniquely identify individual tuples. Minimal superkeys are referred to as candidate keys. Candidate keys are considered minimal because they should only include a minimum number of attributes to uniquely identify individual tuples. For example, a car database may use the vehicle identification number VIN and the make of the vehicle attributes as a candidate key. Another possible candidate key could be obtained by using the license plate and state of the vehicle. Either one of the candidate keys can be selected as a primary key, which then provides a unique identifier for each table record, Table 8.2. A constraint on the primary key is called a key constraint and provides a unique value, assigns a default value to a column if none is specified, and checks for predefined conditions before inserting the data. License number, engine serial number, make, model year. Texas ABC 739, a 69,352 Ford Mustang 02. Florida TVP 347B 43,696 Oldsmobile Cutlass 05. New York MPO 22 X80 3554 Oldsmobile Delta 01. California 432 TFY C 43,742 Mercedes 190D99. California RSK 629 Y80 2930 5 Toyota Camry 04. Texas RPN 624 U028 365 Jaguar XJS 04. Table 8. Two primary key example in a car table for RDBMS. The primary key in a table is typically underlined. Structured query language. The declarative language used in managing and querying structured data in a RDBMS is called Structured Query Language, SQL. SQL implements the four sublanguages mentioned earlier, DDL, DML, DQL, and DCL. SQL is based on relational algebra with many extensions. SQL supports primary keys, foreign keys, inserting data, deleting data, updating data, indexing, recovery, concurrency, and security. SQL focuses on efficiency in addition to specifying the data needed. The main commands in SQL are create table, which is used to create a new table in a database such as create table student, ID int, last name varchar 255, zip code int, which will create a table name student with 3 columns, ID, last name, and zip code. Drop table is used to drop an existing table in a database, and alter table, which is used to add, delete, or modify columns in an existing table. SQL schemas contain tables, i.e., relations, and the RDBMS catalog stores these schemas. SQL constraints are used to specify rules for the data in a table to ensure the accuracy and reliability of that data. There are additional features of SQL such as triggers, views, nested recursive queries, privileges, and metadata. Relational algebra. The theoretical framework for querying relational databases that uses unary and binary operators on relations to manipulate and retrieve tuples is called relational algebra. The following set of relational algebra operations is a complete set: select, project, union, rename, difference, and Cartesian product. It is a complete set because any relational algebra operation can be expressed as a sequence of operations from this set. Relational algebra operators include set operators and relational operators. The set operators include union, intersection, difference, and product, which are all binary operators because they use two relations as operands and produce a new relation as a result. In some cases, the operand relations need to be union compatible, which implies that they have the same number of attribute types defined on the same domains. In what follows, we represent a relation as R and its cardinality or number of tuples as R. Union operator. The union operator applied to two union-compatible relations P and Q results into a new relation, letter 1 D445 equals letter 1 D443 letter 1 D444. So, letter 1d445 equals letter 1d461, letter 1d461, letter 1d443, letter 1d442, letter 1d445, letter 1d461, letter 1d444. With max, letter 1d443, letter 1d444, less letter 1d445, less letter 1d443, plus letter 1d444. The resulting relation R consists of the tuples that either belong to P or Q, or both. Duplicate tuples are eliminated. Intersection operator. The intersection operator, applied to two union-compatible relations P and Q, results in a new relation R equals PQ. Such that letter 1d445 equals letter 1d461, letter 1d461, letter 1d443, letter 1d434, letter 1d441, letter 1d437, letter 1d461, letter 1d444. With 0 less letter 1d445, less min letter 1d443. Letter 1d444. The resulting relation R consists of the tuples that belong to both P and Q. Difference operator. The difference operator applied to two union-compatible relations P and Q results in a new relation R equals P, Q. Such that letter 1d445 equals letter 1d461, letter 1d461, letter 1d443, letter 1d434, letter 1d441, letter 1d437, letter 1d461, letter 1d444. With 0 less letter 1d445, less letter 1d443. The resulting relation R consists of the tuples that belong to P but not to Q. Note that when using the difference operator, the order of the operands is important because it concerns a non-commutative operation. Product operator. The product operator, also known as the Cartesian product, cross product, or cross-join operator, returns the Cartesian product of two relations. Consider the following two relations: a supplier relation P and a product relation Q. The Cartesian product of both relations consists of all possible combinations of tuples from P and Q. The resulting relation R equals P times Q consists of a set of tuples R equals PQ. Such that letter 1d445 equals letter 1d45f equals letter 1d45d, letter 1d45e, letter 1d45d, letter 1d443, letter 1d434, letter 1d441, letter 1d437, letter 1d45e, letter 1d444. With letter 1d445 equals letter 1d443 times letter 1d444. The relational operators are select, project, rename, join, and division. The select, project, and rename operators are unary operators because they only use one operand. The join and division operators are binary operators because they use two operands. Select operator. The select operator is used to return a subset of tuples of a relation based on a selection condition. The latter can consist of predicates combined using Boolean operators, and or not. Every predicate consists of a comparison between the values of two domain-compatible attribute types, or between an attribute type and a constant value from the domain of the attribute type. The result of applying a select operator with a selection condition S on a relation P can be represented as R equals letter 1d70e, letter 1d446, P. With select operator, letter 1d70e. Project operator. The project operator is used to project a relation on a list of attribute types. The result of applying a project operator with a list L on a relation P can be represented as R equals letter 1d70b, letter 1d43f, P. With project operator, letter 1d70b. Note that applying a project operator to a relation results in a vertical subset of the relation with letter 1d445 less or equal to letter 1d443. Because duplicate tuples will be eliminated. Rename operator. The rename operator is used to rename an attribute type of a relation, in case, for example, naming conflicts can occur. The result of applying a rename operator on a relation P to rename attribute type B to it can be represented as R equals row of bytes P. With rename operator row. Join operator. The join operator allows combining tuples of two relations based on specific conditions, also called join conditions. The result of a join is the combined effect of a Cartesian product, times, and selection. The result of applying a join operator to two relations P and Q with join condition, J, can be represented as follows. Letter 1d445 equals P, JQ. with join operator and join condition J. The resulting relation R consists of a set of combinations of PQ tuples such that a combined tuple RR is characterized by R equals letter 1D45D letter 1D45E, P letter 1D434, letter 1D441, letter 1D437, Q letter 1D434, letter 1D441, letter 1D437J. With letter 1D445, less letter 1D443 times letter 1D444. Division operator. The division operator is a binary operator that divides a relation P by a relation Q with QP. The result of a division operator can be represented as R equals P divided by Q. With division operator, the resulting relation R includes all tuples that belong to P combined with every tuple in Q. Note that the division operator is not directly implemented in SQL. The select, sigma, project pi, difference, product times, and union operators are often referred to as the 5 primitive operators because all other relational algebra operators can be derived from them, derived operators. SQL also allows aggregate functions and grouping operations. For join operations, there are many options, such as the following. A theta join allows merging two tables based on a theta condition. Theta refers to the comparison operator in the join condition. Depending upon theta, these joins can be distinguished: greater than join, less than join, greater than or equal join, less than or equal join, and an equijoin if an equals occurs. An equijoin combines tables based on matching values in specified columns. It is equivalent to a theta join, with theta being the equal comparison operator in the join condition. A natural join creates an implicit join based on the common columns in two tables. It is a variant of the equijoin in which one of the shared join attribute types is removed from the result. An inner join represents the intersection of two tables. All joins discussed thus far are inner joins because they do not include tuples lacking corresponding join values in the result. An outer join represents the union of two tables. The outer join operator will also include tuples lacking corresponding join values in the result. A distinction can be made between a left outer join, right outer join, and full outer join. A left outer join includes all tuples from the left relation, P, in the result, either matched with a corresponding tuple from the right relation, Q, based on the join condition, or augmented with null values in case no match with a tuple from Q can be made. A left outer join can be represented as letter 1D445 equals P, JQ. A right outer join includes all tuples from the right relation, Q, in the result, either matched with a corresponding tuple from the left relation, P, based on the join condition, or augmented with null values in case no match with a tuple from P can be made. A right outer join can be represented as letter 1D445 equals P, JQ. A full outer join includes all tuples from P and Q in the result, either matched with the counterparts according to the join condition, or augmented with null values in case no match can be found. A full outer join can be represented as letter 1D445 equals P, JQ. An example of data structure representation for the relational algebra expression is a query tree. Tuple relational calculus and domain relational calculus. In a relational database, a tuple is one row with a collection of values separated by a comma and enclosed in parentheses. An example of a tuple in Python represents the employee Smith, his phone number, age, and zip code. Tuple equals Smith, 8,882,355,151, 50, 48,505. Data inside a tuple can be of any type such as integer, string, float value, or a tuple type. Tuple relational calculus uses tuple variables as key building blocks. A tuple variable refers to a tuple of a corresponding relation, also called range relation. A tuple relational calculus expression specifies a range relation for each tuple variable, a condition to select, combinations of tuples, and a list of attribute types from which the values should be retrieved. As a result, a tuple relational calculus expression looks as follows: T, I, cond T, whereby T represents the tuple variable, AI the attribute type of which the value needs to be retrieved, and cond T, the range relation and extra conditions to select relevant tuples. Consider the following example: T student ID, T student name student T, and T student program equals 3. A condition is specified using a well-formed calculus formula WFF, which can consist of various predicate calculus atoms combined using Boolean operators, and or not. The result of applying a formula to a tuple of a range relation can either be true, false, or unknown. If the result is true, the tuple will be selected in the result. Relational calculus also includes quantifiers such as the existential quantifier, or EXISTS, and universal quantifier, or for all. A formula with an existential quantifier evaluates to true if at least one tuple satisfies it. A formula with a universal quantifier evaluates to true if every tuple from the range relation satisfies the conditions stated. Instead of tuple variables, domain relational calculus defines domain variables that range over single values of domains of attribute types. A domain calculus expression for a relation of degree n looks as follows: 1 v2 vn cond v1 v2 vn v1 v2 vn cond v1 v2 vn, where v1, v2, vn represent the domain variables that range over domains of attribute types, and co and d represents the extra conditions. The earlier tuple relational calculus query, selecting the student ID and student name of all students who study in program number 3, would now look as follows. AB student upda and e equals 3. In this case, we defined 5 domain variables as for the domain of student ID, B for the domain of student name, C for the domain of student address, D for the domain of student city, and E for the domain of student program. The condition E equals 3 is a selection condition. The existential quantifier, or EXISTS, and universal quantifier, or for all, are also supported in domain relational calculus. Query by example QBI language. The relational database language based on domain relational calculus is called query by example QBE. QBE queries are expressed via graphical query language using visual tables where the user enters commands, example elements, and conditions. A parser converts the QBE graphical queries into statements expressed in a database manipulation language, such as SQL. Logical design. The process of logical design involves designing a database based on a specific data model, but independent of physical details. The logical design for a relational DBMS includes specifications for tables, relationships, and constraints. The logical design is performed in 4 steps. Map conceptual model to logical model components. Validate the logical model using normalization, validate logical model constraints, and validate the logical model against user requirements. To determine the quality of relation schema design, we follow the informal design guidelines for relational schemas and use simple measures of quality such as making sure attribute semantics are clear, reducing redundant information, and reducing null values. Null values cause redundant work, which wastes storage space and increases the difficulty of performing operations. Technology in everyday life. RDBMS. Airplanes have to be designed and tested for safety. Airplane wings are complex items that include a large number of parts, come in various shapes and forms, e.g., rectangular wings for small airplane, elliptical wings, tapered wings, and trapezoidal wings, and require multiple designers to collaborate on their design. Airplane wings are typically designed using computer-aided design, CAD, software systems that use data management systems to store and retrieve data. Is a RDBMS the best solution to store and retrieve these types of items? Why or why not? Are there other, better ways to track the development, design, and testing of mechanical parts crucial to passenger safety? Relational model constraints. The constraints that ensure database correctness are called relational model constraints in DBMS. The different types of constraints are domain, uniqueness, key, and entity integrity constraints. The domain constraint defines the domain of values for an attribute. The uniqueness constraint specifies that all the tuples must be unique. The key constraint specifies that all the values of the primary key must be unique. The entity integrity constraint specifies that no primary key contains a null. Additionally, functional dependency, FD, is a constraint that specifies the relationship between 2 sets of attributes and provides a formal tool for the analysis of relational schemas. FDs enable the detection and description of business rules in precise terms. FDs can be used to help normalize relational schemas. A multivalued dependency, MVD, occurs when 2 attributes in a table are independent of each other, but both depend on a third attribute. MVDs are required to achieve higher forms of normalization, e.g., for NF. The normalization process can be automated using algorithms that can convert a given relation into sets of relations in a given normal form. Normalization. The process of structuring a relational database to reduce data redundancy and improve data integrity is called database normalization. A normal form applies to a table relation, not to the database. The main types of normalization are: first normal form 1NF, second normal form 2NF, third normal form 3NF, Boyce-Codd normal form BCNF, and fourth normal form 4NF. There are additional normal forms, which are more complex. Each cell in 1NF must contain only a single atomic value, and every column must be uniquely named. The relational model requires tables to be in 1NF form. Tables in 2NF must be in 1NF and not have any partial dependency. Tables in 3NF must be in 2NF and have no transitive functional dependencies. BCNF is a higher version of the 3NF and is used to address the anomalies. Tables in 4NF must be in BCNF 3NF and not have MVDs. The following example converts a table to 1NF, 2NF, and then 3NF. Table 8. 3 contains the original data, that is then converted to 1NF, Table 8.4, 2NF, Table 8. 5 and 3NF, Table 8.6, Table 8.7, and Table 8. 8. It is assumed here that the customer name is a composite attribute that contains first name and last name, and therefore must be broken down into its component attributes to be stored in a relational table that satisfies 1NF. Customer name item 1 item 2. Cheryl Adam milk bread. Jeff Mark juice water. Rana Park bread milk. Table 8 3 data table. First name last name item 1 item 2. Cheryl Adam milk bread. Jeff Mark juice water. Rana Park bread milk. Table 8. 4 table converted to 1NF. First name last name item. Cheryl Adam milk. Cheryl Adam bread. Jeff Mark juice. Jeff Mark water. Rana Park bread. Rana Park milk. Table 8. 5 table converted to 2NF. Customer ID first name last name. 1 Cheryl Adam. 2 Jeff Mark. 3 Rana Park. Table 8. 6 table converted to 3NF. Customer item ID item. 1 milk. 2 bread. 3 juice. 4 water. Table 8. 7 table converted to 3NF. Item. Customer ID item ID. 1 1 1 2 2 3 2 4. Table 8. 8 table converted to 3NF. Relational table. Relational database design. Modeling data into a set of tables with rows and columns is called relational database design, RDD. Each row represents a record, and each column represents an attribute. RDD includes 5 phases. Requirements analysis phase to assess the informational needs of an organization. Logical design phase to create a conceptual model, entity relationship based on phase 1. describes interrelated attributes in a specific domain of knowledge. Physical design phase to maximize database efficiency, unified modeling language UML helps developers visualize the relationships between the different pieces. Implementation phase to convert the tables developed in the diagram into SQL. Monitoring and maintenance phase to ensure that RDBMS is functioning properly. Industry spotlight. RDBMS and banking. RDBMs are ideal in banking applications for tracking and storing account numbers, orders, and payments. Most banks run Oracle applications because of the powerful integration of technology and business applications. Oracle includes built-in functionality that is designed specifically for banks such as Oracle Banking Platform, which is the leading choice for banks looking to change their core systems for customer-centric retail banking. Mapping a conceptual EER model to a relational model. After designing the diagram, we need to convert it to relational models that can be directly implemented by any RDBMS. modeling helps create a conceptual model that relies on entities and their interrelationships. The degree of a relationship establishes how many entities it interrelates. Therefore, relationships can be unary, binary, ternary, and more generally n-ary. Cardinality ratios are used to specify how many tuples are interrelated as part of a binary relationship, i.e. 1n, n1, mn. Multi-valued attributes are allowed in models. They are used to represent an attribute that contains a list of values. For example, a car entity may have a color attribute that is multi-valued and include a list of all the car colors. In modeling, a weak entity is a type of entity that cannot be uniquely identified based on its attributes alone and must rely on a strong entity to provide the context necessary for identification. For example, an employee in a company may have dependents for health insurance purposes. In this case, a dependent entity is a weak entity, and the ID of the employee, who is the strong entity, needs to be used to fully identify a dependent. The following steps must be followed to map an EER model to a relational model. Mapping of regular entity types. Create a table that includes all of its simple attributes and select one of the key attributes as the primary key. If the key chosen is from a composite attribute in the EER model, the corresponding set of simple attributes will together form the primary key. Mapping of weak entity types. For each weak entity, create a table that includes all of its simple attributes, and include the attributes that make up the key of the associated strong entity. The primary key in this case is the combination of the primary key of the associated strong entity and the partial key of the weak entity, if any. Mapping of binary 1 relation types. One solution is to create a relation for each participating entity, choose a primary key in one of the two relations, and make a foreign key referencing the primary key in the second relation. In some cases, it is more appropriate to merge both relations from the participating entities into one or create a cross-reference, i.e., relationship relation between the two relations. Mapping of binary 1 relationship types. Create a relation for each participating entity. The primary key from the one side of the relationship is added to the many side as a foreign key. An alternative approach is to use a relationship relation, but it is rarely done. Mapping of binary n relationship types. Create a relation for each participating entity. Also create a relationship relation and include as foreign keys attributes the primary keys of the relations that represent the participating entity types. Their combination will form the primary key of the relationship relation. Mapping of multivalued attributes. For each multivalued attribute, create a new relation that includes an attribute corresponding to the multivalued attribute in the original entity type, and include as a foreign key the primary key of the relation that represents the entity that includes the multivalued attribute. The primary key in the new relation created is the combination of the attribute that corresponds to the multivalued attribute in the original entity type and the foreign key. Mapping of NRE relationship types. Create relationship relations for each NRE relationship and include as foreign keys attributes the primary keys of the relations that represent the participating entity types. Mapping specialization or generalization. Convert each specialization with M subclasses, S1, S2, SM, and generalize superclass C, where the attributes of C are K, A1, and in K is the primary key, into relational schemas using one of the four following options. Option 8A, multiple relations superclass and subclasses. Option 8B, multiple relation subclass relations only. Option 8C, single relation with one type attribute. Option 8D. Single relation with multiple type attributes. Mapping of union types. For mapping a category whose defining superclass has different keys, it is customary to specify a new key attribute, called a surrogate key, when creating a relation to correspond to the category. Physical design. Attributing logical concepts to physical constructs is called physical database design. The input to the physical design step is a logical representation of the system. It is a joint responsibility of the database designer and DBA. The main responsibility of the physical design is optimizing performance while ensuring data integrity. The main issues addressed in physical design are storage media, file structures, and indexes. The database is stored on a disk using a standard file system, not one tailored to the database. The database runs on an unmodified general-purpose operating system, disk storage, and basic file structures. Database tables are stored in disk storage, which is the memory device that stores the data, such as hard disks, flash memory, magnetic disks, optical disks, and tapes as shown in Figure 8. 9. The records in the tables could be of fixed length, which means the records are exactly the same length, or variable length, which means the records differ in their length. All records are classified into blocks, and the length of the record can exceed the size of a block, which is called a span record. Assume that each relation is stored as a file, and each tuple is a record in the file. The files could be ordered, i.e., the records are sequenced on some field, or unordered, i.e., the records are not in any order. The average record access time is the average time taken for a system to access the record. A redundant array of inexpensive disks, RAID, stores information across an array of low-cost hard disks. Triangle diagram. primary storage from top down, CPU registers, caches, central storage, I/O boundary separates middle, secondary storage in lower half, HDD, SSD and tape, optical media. Figure 8.9 This storage hierarchy includes primary and secondary storage. Attribution, copyright Rice University, OpenStax under CC by 4. 0 License, physical file organization and indexing. File organization and indexing are used to minimize the number of block accesses for frequent queries. There are many types of file organization, with the most popular being sequential, relative, and indexed organization. In a sequential file organization, records are organized in the order they are stored, and any new record is added at the end. In a relative organization, each record is assigned a numeric key to rearrange the order of the records at any time. Similar to the relative organization, indexed organization uses a key, but the key is unique and fixed. In addition, there are many other file organization types such as heap, hash, B+, and cluster file organization. A heap in file organization refers to an unordered collection of records where new records are placed wherever there is free space and no particular ordering is enforced. Figure 8.10 shows an example of a heap file organization. Illustration depicting records at left and data blocks in memory at right blocks 1-4. New record is shown being inserted into a data block in memory. Figure 8.10 This heap file organization example shows how to insert a new record, record 4, into the data blocks in the memory. Attribution, copyright Rice University, OpenStax under CC by 4. 0 License, physical database organization. A tablespace is where tables are stored physically in the memory, i.e., the physical container of database objects. The use of tablespaces has an impact on physical database design concerning intraquery parallelism, where different subsets of data can be searched in parallel for a complex query, and interquery parallelism, i.e., many simple queries executed in parallel, query execution concepts. Processing the query includes 5 steps: parsing, checking the syntax of the query, users' privileges, table and attribute names. Translation, translating from high-level language to machine language. Optimizer, selecting the best plan to execute. Execution, running the selected plan. Evaluation, returning the query result. The query optimizer determines the lowest cost strategy for query execution using the internal representations of a query, i.e., query tree and query graph. The mathematical technique for processing the query quickly is called heuristics optimization. The main heuristic is to first apply the operations that reduce the size of intermediate results. Physical database design and tuning. Assume you are looking for a specific record in a huge database and that the record you are looking for is at the end. To retrieve that record, the system moves sequentially record by record and takes a long time to process. Let us follow this SQL exercise using Table 8.9 Employee. Number F name L name country. 1 Sam Smith, USA. 2 Adam Bell, UK. 3 Matt John, USA. 4 John Zach, USA. 5 Andy Dave, UK. Table 8.9 Employee Table. We are looking for Andy using the following SQL statement. Select from employee where fname equals Andy. Looking for Andy takes 5 comparisons because Andy is at the end of the table. However, if we sort the data alphabetically, Table 8.10, searching for a name happens faster 2 comparisons. Employee sort. Fname L name index. Adam Bell 2. Andy Dave 5. John Zach 4. Matt John 3. Sam Smith 1. Table 8.10 Employee sort table. An index holds the field being sorted and points from each record to the corresponding record where the data are stored, figure 8.11. Tables for employee sort and employee are visible with arrows connecting index column from employee sort table to number in employee table, figure 8.11. Using indexing can improve the query performance. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Indexing helps improve the performance of the query process. Creating an index in SQL retrieves data from the database more quickly. The following are SQL syntaxes for creating an index and creating a unique index. Note that a unique refers to an index where all rows of the index must be unique. That is, a row may not have identical non-null values for all columns in this index as another row. Create index name on table name, column 1. Create unique index name on table name, column 1. In addition, you can delete the index anytime using the drop statement. Drop index name on table name. A key is needed to index an attribute. However, an index can be constructed with one or multiple attributes. If a table requires more than one index, we need to decide which attribute we cluster. In general cases, the indexing is implemented using binary tree, B tree, or B plus tree. In practice, B plus trees are more commonly used in database systems. Binary tree is a tree in which every node has up to 2 children. B tree generalizes the binary tree with more than 2 children and may have 1 child. B plus tree is a tree with a large number of children per node, but in some cases it is more efficient to use hash indexing, e.g., equality conditions. The normalized database is the database with eliminating data redundancy to enhance the data integrity in the table. Denormalization is a strategy to increase the performance of a normalized database. It adds redundant data such as extra attributes, adds new tables, or creates instances. The main goal is to decrease the running time of queries by making data more accessible. Then gets through the relational model and constructors. The relational model uses 2 types of constructors. One is aggregate of, which enables the creation of tables by aggregating various columns that contain data of different types. The other is set of, which enables the gathering of multiple records within a table. Is there a limitation with this approach? RDBMS APIs and programming techniques. A database architecture is a representation of the design that helps design, develop, implement, and maintain the DBMS. This section covers RDBMS architectures, database APIs, object persistence and object relational mappings, ORMs, and sample RDBMS applications. RDBMS architectures. A relational database management system, RDBMS architecture, is categorized as a centralized system architecture and a tiered system architecture. In centralized system architecture, the DBMS's responsibilities are handled by one centralized entity, the mainframe database, which has become rare, expensive, and difficult to maintain. The tiered system architectures aim to decouple the centralized setup by combining the computing capabilities of powerful central computers with the flexibility of personal computers, PCs. There are multiple variants of the tiered system architecture, such as 2-tier architecture or client-server architecture. The fat client variant is where presentation logic and application logic are handled by the client and is common in cases where it makes sense to couple an application's workflow with its look and feel. In that case, the DBMS now fully runs on the database server. A thin client variant is one where only the presentation logic is handled by the client and applications and database commands are executed on the server. It is common when application logic and database logic are tightly coupled or similar. 3-tier architecture decouples application logic from the DBMS and puts it in a separate layer, i.e., application server. Note: application server or database server may consist of multiple physical distributed machines, database APIs. In a tiered DBMS system architecture, client applications can query database servers and receive results. It is possible to use in-process DBMSs, e.g., SQLite, or access standalone DBMS servers, e.g., Postgres. Client applications that wish to utilize the services provided by a DBMS use a specific API provided by the DBMS. This database API exposes an interface through which client applications can access and query a DBMS. The database server receives calls made by clients and executes the relevant operations before returning the results. In many cases, the client and server interfaces are implemented to work over a computer network using network sockets. The main goal of a database API is to expose an interface through which other parties can utilize the services provided by the DBMS. Most DBMS vendors provide a proprietary, DBMS-specific API. The disadvantage is that client applications must be aware of the DBMS that will be utilized on the server side. Alternatively, generic, vendor-agnostic universal APIs have been proposed, and they allow to easily port applications to multiple DBMSs. APIs can be embedded or call-level. Embedded API embeds SQL statements in the host programming language, meaning that SQL statements are part of the source code. Before the program is compiled, a SQL precompiler parses the SQL-related instructions and replaces them with source code instructions native to the host programming language used. Converted source code is then sent to the actual compiler. Call-level APIs, SQL CLI, work by passing SQL instructions to the DBMS by means of direct calls to a series of procedures, functions, or methods as provided by the API to perform the necessary actions, e.g. ODBC JDBC, Object Persistence and Object Relational Mappings, ORMs. API technologies such as JDBC and ADO.NET represent database-related entities, e.g. tables, records in an object-oriented OO way, as plain domain entities such as book and author are represented as objects using a programming language's representational capabilities and syntax. Object persistence ensures that the corresponding object data are persisted behind the scenes to a database or other data source. Language-integrated query technologies apply similar ideas, while object persistence APIs go a step further as they also describe the full business domain, i.e. the definition of data entities within the host language. They allow for efficient querying of objects. Such entities are frequently mapped to a relational database model using an Object Relational Mapper, ORM. It is not strictly necessary to utilize an ORM to enable object persistence, though most APIs tightly couple both concepts. Sample RDBMS applications. On the web, there are two types of calls, asynchronous and synchronous. In the asynchronous call, the client sends a request without waiting for a response. In the synchronous call, the client sends a request and waits for a response from the service. API and HTTP calls are examples of synchronous calls. An example of a database fully managed on the web is Oracle's NoSQL Data Services. RDBMS features. RDBMS includes multiple features such as transaction management, concurrency control, data distribution, distributed transaction management, distributed and parallel processing, recovery, and security. Transaction management. Most database systems are multi-user, while transaction management allows concurrent access to the same data by multiple users. It may induce different types of anomalies. As a result, errors may occur in the DBMS or its environment. RDBMS must ensure that transactions support ACID, atomicity, consistency, isolation, durability properties as explained in the following paragraphs. A transaction is a set of database operations induced by a single user or application that should be considered as one undividable unit of work, e.g., transfer between two bank accounts of the same customer. A transaction either succeeds or fails in its entirety. A transaction renders the database from one consistent state into another consistent state. The transaction manager supervises the execution of database transactions. A database transaction is a sequence of read-write operations considered to be an atomic unit. The transaction manager creates a schedule with interleaved read-write operations, guarantees ACID properties, and can commit a transaction upon successful execution or roll back a transaction upon unsuccessful execution. Delineating transactions within the transaction lifecycle is called transaction management. Various components are involved in transaction management, i.e. scheduler, recovery manager, stored data manager, and buffer manager, and RDBMSs use a log file to register the current state of the transaction, active, committed, or aborted, and facilitate the implementation of checkpoint for rollback purposes. Concurrency control. The coordination of transactions that execute simultaneously on the same data so that they do not cause inconsistencies because of mutual interference is called concurrency control. A lock manager provides concurrency control, which ensures data integrity at all times. The two types of locks are read locks and write locks. The lock manager is responsible for assigning, releasing, and recording locks in the catalog. The lock manager makes use of a locking protocol that describes the locking rules and a lock table that contains the lock information. Concurrency problems occur when multiple transactions execute concurrently without control. Data distribution. The process of storing data in more than one site to improve the data availability and retrieval performance is called data replication. Multiple databases located at different sites may need to be synchronized in real time to ensure consistency and optimal performance. E.g., fragmentation. There are different types of fragmentation. Vertical fragmentation consists of a subset of columns of data. Global view can be retrieved with join query. Useful if only some of a tuple's attributes are relevant to a node. Horizontal fragmentation, sharding. The fragment consists of rows that satisfy a query predicate. Global view can be retrieved with union query. Common in NoSQL databases. Mixed fragmentation combines horizontal and vertical fragmentation. global view can be retrieved with join plus union query. Distributed transaction management. A distributed transaction is a set of operations that are performed across multiple database systems. Distributed transaction management coordinates the resources between multiple databases. The transaction manager decides whether to commit or roll back a transaction using a TOOF is commit to PC. The steps of 2PC are described in Figure 8.12. Distributed transaction request steps, system to database A. Prepare to commit request, database B. Prepare to commit response, database A. Commit request, database B. Commit response, database A. Distributed transaction response system. Figure 8.12 two-phase commit protocol illustrates the 6 steps needed for a distributed transaction. Attribution, copyright Rice University, OpenStax, under CC by 40 license. The transaction management server manages the transactions in loosely coupled and tightly coupled modes. In loosely coupled, the different database servers coordinate transactions without sharing resources. In the tightly coupled, resources are shared, parallel and distributed processing. Many databases, including NoSQL, use parallel processing, a technique in which multiple processors work simultaneously on different tasks or different parts of a task to enable concurrent processing of large amounts of data. Distributed database systems distribute data and data retrieval functionality over multiple data sources or locations. Figure 8.13 shows different architectures of distributed databases. In shared memory architecture, multiple interconnected processors that run the DBMS software share the same central storage and secondary storage. With shared disk architecture, each processor has its central storage, but shares secondary storage with other processors using a network-attached storage, NAS, or storage area network, SAN. In shared nothing architecture, each processor has its central storage and hard disk units, and data sharing occurs through the processors communicating with one another over the network. Illustration of parallel processing of tasks of different architectures of distributed data, shared memory architecture, shared disk architecture, and shared nothing architecture. Figure 8.13 The different distributed architectures are shared memory architecture, shared disk architecture, and shared nothing architecture. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Scalability is the measure of a system's ability to scale, increase, or decrease the performance and/or cost in response to any system change. Scalability can be achieved through vertical scalability, where the capacity of each node can be increased, and horizontal scalability, in which more nodes can be added. Parallel databases focus on data distribution for performance and intraquery versus interquery parallelism. Federated databases use nodes in a shared nothing architecture, each running an independent DBMS instance with horizontal data fragmentation. In distributed query processing, the optimizer should not only consider the elements of a standalone setting, but also the properties of respective fragments, communication costs, and location of the data in the network. Metadata may also be distributed, both globally across all nodes and locally within a single node. Query optimization is needed. Recovery. The activity of setting the database in a consistent state without any data loss in the event of a failure, or when any problem occurs, is called database recovery. System failure occurs when a system goes down in the middle of a transaction, and media failure occurs when a database file or the device storing the database file stops working. There are many recovery techniques such as mirroring by adding 2 complete copies of the database, transaction logs by recording the transitions changes, shadow paging by dividing the database into pages, and backups. Backups are the most used method for recovery and include immediate backup and archival backup. An immediate backup stores the copies in disks, and an archival backup stores the data in different server sites. Security. Using a set of controls to secure data, guaranteeing a high level of confidentiality, is considered database security. Security issues facing a database include human errors such as password sharing and weak passwords. SQL injection, which involves the use of SQL attack strings in database queries. Overflow attacks, which writes a large amount of data to a fixed-length block of the memory, causing overflow. Denial of service attacks, DoS, that use a large amount of requests to crash the server, and internal and external attacks. Figure 8.14. Illustration. Attacker connects to website through Web API server with malicious SQL query. Data is returned through Web API server to attacker along with data of all teachers. Figure 14. SQL injection gives attackers access to confidential client data such as teacher data. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. To secure the database, there are many methods such as discretionary access control, which may grant or reject object access using a set of policies. Mandatory access control, which restricts the ability to grant or reject access to resource objects. Statistical database security, which focuses on the protection of statistical values stored in the database. Encryption, which converts the data into secret code to hide the true meaning. And public key infrastructure, which is a set of roles and policies needed to manage the database. Link to learning. There are many places on the internet where you can learn more about programming and databases. For example, should you want to build your own website, you will need to know something about structured query language, SQL, which is a standard language for accessing and manipulating databases. Visit an introduction to SQL to help you better understand SQL, what SQL can do, and how to use SQL when building a website. Learning objectives. By the end of this section, you will be able to discuss the various types of legacy database management systems, explain the functionality of non-first normal form (NFNF) database management systems, identify various characteristics of object databases and object persistence, differentiate the various relational database management system extensions, describe XML databases, summarize unstructured data and the advent of not only SQL, NoSQL databases, differentiate cloud-related data management services and other types of databases. A non-relational database is a database that does not use a traditional method for storing data such as rows and columns. Instead, non-relational databases use a different storage model with specific requirements based on the type of data being stored. Relational databases typically store data in tables, with columns representing the attributes of the data and rows representing individual records. This structure is optimized for fast retrieval and manipulation of data using SQL queries. In contrast, non-relational databases are optimized for storing and querying large amounts of data and are typically stored in a specialized format that allows for efficient indexing and querying. This format may include the use of columnar storage and compression techniques. Legacy databases. Flat file database and multi-file relational database are the two main legacy DBMSs. A flat file database uses a simple structure to store data in a text file. Each line in the file is holding one record. A multi-file relational database is more flexible than flat file structures as it provides more functionality for creating and updating data. It contains multiple tables of data with rows and columns that relate to each other. Hierarchical model. A hierarchical model is a model in which data are stored in the form of records and organized into a tree structure. The structure is parent-child, and each parent may connect to one or more child nodes, as in Figure 8.15. As an example, IBM IMS is a hierarchical database management software system for OLTP. Root parent hierarchy chart with child A, child A1, child A2, child B, child B1, child C, child C1, child C2, child C3. Figure 8.15. A hierarchical model shows a root parent connected to three child nodes. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. A hierarchical model has many limitations such as the complexity of navigating the system, its requirement that data be repetitively stored due to a tree-like structure with a high level of redundancy, and its need for sequential searching. Non-first normal form DBMSs. The database data model that does not meet any of the conditions of database normalization defined by the relational model is called a non-first normal form, NFNF. However, data in this form may require complex joins, which can make querying more complicated, although it does not lead to data duplication. Object databases and object persistence. An object-oriented database management system, OODBMS, offers unique object identifiers to access each object. The persistence is established with time and space, and the object exists even after its parent object has been deleted, which means it is persistent with time. An example of an OODBMS is DB40, which is an open-source embeddable object database for Java and .NET environments. It allows developers to store and retrieve objects directly rather than having to map objects to a relational database schema. Principles of object persistence. When an object is not deleted until a need emerges to remove it from memory, object persistence appears. In other words, the transient object is only needed during program execution and can be discarded when the program terminates. Persistence strategies include persistence by class, persistence by creation, persistence by marking, persistence by inheritance, and persistence by reachability. In persistence orthogonality, the environment does not require any actions by a program to retrieve or save their state. In persistence independence, an object is independent of how a program manipulates it. There are many types of orthogonality. For example, all objects can be made persistent irrespective of their type or size, and they can achieve transitive persistence, refers to persistence by reachability. Persistent programming languages extend an OO language with a set of class libraries for object persistence. Serialization translates an object's state into a format that can be stored, for example, in a file and reconstructed later. OODBMSs and ODBs. OODBMSs appeared around 1985 and originated as extensions of OO programming languages. Object-oriented programmers store the developed products as objects and modify existing objects to make new objects within the OODBMS. OODBMSs store persistent objects in a transparent way, support persistence orthogonality, and guarantee the ACID properties. OODBMS has many limitations such as lack of a universal data model, lack of experience compared to RDBMS, lack of support, and complexity. The Object Data Management Group, ODMG, was created in 1991 and is based on Object Management Group, OMG, standard. Its main idea is to create a set of specifications to develop applications for an object database. There have been 5 revisions of ODMG, and the last version is ODMG 3.0. Most mainstream database applications are built using an OO programming language in combination with an RDBMS rather than using an object relational mapping, ORM. Industry Spotlight. MongoDB. MongoDB is the most popular NoSQL database. It has delivered substantial values for some businesses that have been struggling to handle their unstructured data with the traditional RDBMS approach. After MetLife spent years trying to build a centralized customer database on an RDBMS that could handle all its insurance products, someone at an internal hackathon built one with MongoDB within hours, which went to production in 90 days. Extended Relational Databases. Extended Relational Databases, ERDBMSs, combine characteristics of RDBMS and OODBMS. The products of ERDBMSs provide a relational data model and query language that have been extended to include features of OODBMSs. Limitations of the relational model. The relational model has a flat structure, and expensive joins are needed to defragment the data before it can be successfully used, which increases the complexity of the objects due to normalization. Specialization, categorization, and aggregation cannot be directly supported. A tuple constructor can only be used on atomic values, while a set constructor can only be used on tuples. However, both constructors are not orthogonal, cannot model behavior or store functions, and both provide poor support for multimedia. Active RDBMS extensions. A trigger is a statement consisting of declarative and/or procedural instructions and is stored in the catalog of the RDBMS. Triggers can also reference attribute types in other tables. Triggers are automatically executed when a triggering event occurs, such as any change in the database. Triggers are similar to procedures stored in the database, but differ in that they need to be explicitly invoked. Triggers are easy to code, are useful in the validation process, allow calling other procedures from the trigger, and allow recursion. Object Relational RDBMS extensions. Object Relational DBMSs, ORDBMSs, keep the relation as the fundamental building block and SQL as the core DDL-DML, but they use the following OO extensions. User-defined types, UDTs, user-defined functions, UDFs, inheritance, behavior, polymorphism, collection types, large objects, LOBs, and recursive SQL queries. Technology in everyday life. Non-relational database management system. You are told that a new type of data structure has been unveiled, and that it characterizes new forms of data being collected from sensors located at the edge of the network. Would you conclude that a new kind of non-relational database management system needs to be developed? What would be your approach for selecting the best possible type of non-relational database management system for this application? XML databases. Extensible Markup Language, XML, is a markup language similar to HTML, but users define their tags. Predefined tags such as HTML are not used. The oldest schema language for XML is the Document Type Definition, DTD. An XML schema is the metadata that describes the structure of an XML document. Extensible Stylesheet Language, XSL, defines the features and syntax of XML and consists of a language for transforming XML documents, XSLT, and an XML vocabulary for specifying formatting, XSLFO. An XML namespace is a collection of names that can be used as element names in an XML document. XML Path Language, XPath, uses path expressions to select nodes in an XML document. An XML database is a data persistence system whereby the data are specified and stored in XML format. It is easy to code, but has no universally accepted rules for the XML database. Differences between XML and relational data. While XML data are hierarchical, relational data are represented in a model of relationships. XML data are self-describing, but relational data are not. XML data have inherent ordering, but relational data do not. RDBMS only supports atomic data types such as integer, string, and date. XML DTDs do not support atomic data types. XML schema supports both atomic and aggregated types modeled in object relational databases using user-defined types. XML data are semi-structured, can include certain anomalies, and a change to DTD or XSD necessitates regeneration of tables. For example, suppose a banking application needs to transfer money from one account to another. The transaction may involve multiple steps, such as deducting the amount from the sender's account and adding it to the recipient's account. If any of these steps fail, the entire transaction should be rolled back to ensure that the database remains consistent. Atomicity ensures that the transaction either completes successfully and all the changes are committed, or it fails and none of the changes are committed, leaving the database in a consistent state. Mappings between XML and object relational data. An ontology is semantic data used to describe entities of the real world and the relationship between the entities using the Web Ontology Language, OWL. Figure 8. 16. To convert and map XML data into relational databases, we can use table-based mapping, which copies data from an external source such as XML into the selected table. A database schema is the structure of a database that defines how data are organized within a database. Schema-oblivious mapping stores both OWL class and instance data in a single table, which allows files to be easily parsed and loaded into the database. Schema-aware mapping maps the OWL schema into corresponding tables and then loads the instance data into the selected tables. Chart for service, described by service model, supporting service grounding, and presenting service profile. Figure 8:16. The service profile tells what the service does, the service grounding tells how to access it, and the service model tells how it works. Attribution, copyright Rice University, OpenStax under CC by 4. 0 license. Global issues in technology. IT solutions and security issues. IT solutions can help to address a range of security issues that organizations may face. Some common IT solutions for security issues include encryption and antivirus software. Given the diversity of non-relational database management systems and the fact that multiple systems may sometimes be used as part of the same solution, what are possible security issues that need to be considered? Unstructured data and NoSQL databases. Unstructured data are data that are not arranged according to the data model and cannot be stored in a traditional relational database. NoSQL databases are schema-agnostic and provide the flexibility needed to store and manipulate large volumes of unstructured and semi-structured data. Users do not need to know what types of data are stored during setup, and the system can accommodate changes in data types and schema. Designed to distribute data across different nodes, NoSQL databases are generally more horizontally scalable and fault-tolerant. MongoDB Atlas is an example of a NoSQL database system that is fully managed and operates on the cloud. NoSQL DBMS is not ACID compliant, and data consistency is not guaranteed. NoSQL DBMSs provide eventual consistency instead. When old data are getting overwritten, results that are a little wrong are temporarily returned. For example, Google's search engine index cannot overwrite its data while people are simultaneously searching a given term, so it does not give the most up-to-date results during a search, but it gives the best answer it can. While this setup does not work in situations where data consistency is necessary, such as financial transactions, it is just fine for tasks that require speed rather than pinpoint accuracy. Key value stores. A key value store is a simple database that uses an associative array such as Redis, DynamoDB, and CosmosDB. It stores only key value pairs, provides basic functionality for retrieving the value associated with a known key, and works best with a simple database schema. Tuple and document stores. A tuple and document store database stores data in XML or JSON format with the document name as key and the contents of the document as value. Image of code written in A XML using and B JSON using and figure 8. 17 The same code written in a XML and B JSON shows the differences between the formats. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Documents can contain many different value types and can be nested, making them particularly well suited to manage semi-structured data across distributed systems. For example, MongoDB and Couchbase are document-oriented databases that store data in flexible, schemaless documents, which allows for a high degree of flexibility in how data are stored and queried. However, MongoDB uses a flexible document model that allows for complex nested structures and hierarchical data, while Couchbase uses a key-value data model with JSON documents. This makes MongoDB more suited for complex data structures and Couchbase more suited for simpler data structures. Column-oriented databases. A column-oriented database stores data in column families or tables and are built to manage petabytes of data across a massive distributed system, e.g., Cassandra and HBase. Both Cassandra and HBase use a column family data model to store and manage data and are both NoSQL databases that are designed to handle large volumes of data. However, Cassandra uses a partitioned row store data model, while HBase uses a column-oriented data model. This means that Cassandra is optimized for high-speed reads and writes of individual rows, while HBase is optimized for scanning large tables of data. Graph-based databases. A graph-based database represents data as a network of related nodes or objects to facilitate data visualizations and graph analytics. The graph may represent any relationship such as 1, n, and n. It is useful for analyzing the relationships between heterogeneous data points, such as in fraud prevention or Facebook's friend graph. Other NoSQL databases. There are many NoSQL databases, such as XML databases, OO databases, database systems to deal with time series and streaming events, and database systems to store and query geospatial data. Spatial data refer to data that are associated with a specific location or geographic area. Spatial data can be managed and analyzed using a geographical information system. There are also database systems such as BayesDB. BayesDB is a probabilistic programming platform that is based on a Bayesian approach to modeling data relationships. The structure of BayesDB can be broken down into several key components, including data tables and models that lets users query the probable implication of their data. Transaction management and concurrency in NoSQL databases. With the increasing amount of data, the number of parallel transactions has increased. In this case, the capacity can be increased by extending the system capabilities, vertical scaling, or arranging multiple servers in a cluster, horizontal scaling. NoSQL databases distribute data over a cluster of database nodes for the sake of performance and availability. In many NoSQL implementations, e.g., Cassandra, Google's Bigtable, Amazon's DynamoDB, all nodes implement the same functionality and are able to perform the role of request coordinator using a membership protocol. The membership protocol checks the availability of each node, which makes it easier to apply index between them, but does not guarantee that every node is aware of every other node at all times. Hashing is the process of transforming a key to another value to implement a hash table. Consistent hashing avoids mapping each key to a new node in case nodes are added or deleted. Consistent hashing uses a modulo operator, %, to distribute keys over servers. The syntax is h_key equals key%n, where n is the number of servers. Eventual consistency means the data and their replicas become consistent at some point in time after each transaction. NoSQL databases are categorized as eventual consistency because it guarantees up-to-date information. Therefore, many NoSQL databases guarantee so-called eventual consistency based on the CAP theorem. The CAP theorem states that a distributed computer system cannot attain the following three properties concurrently. Consistency, all nodes see the same data at the same time. Availability guarantees that every request receives a response, indicating a success or failure result. And partition tolerance, the system continues to work even if nodes go down or are added. Then gets through C++ and databases. You are asked to develop a program in C++ that needs to store and retrieve data for later use. Which type of non-relational database management system would you recommend for this application? Query languages and APIs for NoSQL databases. Processing an XML within a database application requires parsing the document and then processing the code using an API such as Document Object Model DOM API. DOM API is a tree-based API, i.e., the memory representation is a tree. Figure 18 shows an example of XML code and the corresponding DOM tree. Information for Adam Nguyen, hired in 2021, in A. Input XML, B. XML tree, and C. DOM tree. Figure 18. This figure visualizes the tree-based DOM API. A shows the input XML code, B highlights in-memory tree representation, and C demonstrates the corresponding DOM tree. Attribution: Copyright Rice University, OpenStax under CC by 4. 0 license. NoSQL databases use filters to apply the simple query. That is, they use variables in the query that are populated on the server. Additionally, most NoSQL databases support complex queries using aggregation with MapReduce. MapReduce is an open-source software framework used to apply complex queries. It implements a map function, which is the conversion of a dataset into a tuple, and reduces function, which reduces the map into a smaller set. Cloud and other data management services. Data as a service, DAS, is a data management technique that uses the cloud to store, process, and manage data. DAS uses web services to handle data located on the internet. Many vendors provide DAS such as Azure, AWS, GCP, and IBM Cloud. Amazon Web Service, AWS, offers many solutions for DAS, such as Aurora, RDS, and Redshift for relational database and DynamoDB for the key-value database. Cloud Data as a Service, DAS. DAS is a data management strategy that includes many technologies such as information lifecycle solutions, data modeling, replication, and content management. DAS is on-demand and subscription-based, which means the customer only pays for the services they need. The functionalities of DAS are data quality, storing, managing, securing, and analyzing data. One of the key advantages of cloud-based database systems is their ability to be elastic and provide compute and storage resources on demand. This means that as the size of a dataset grows or decreases, as more or fewer users access the database, the system can quickly scale up or down its resources to handle the demand. Blockchain DBMSs. The technology that records transitions securely is called blockchain. It has the world's attention because of its use of cryptocurrencies such as Bitcoin. In healthcare, blockchain technology can be used to create a secure and transparent system for managing healthcare data. This can help to improve patient privacy, reduce fraud, and improve the efficiency of healthcare systems. A blockchain DBMS is a database that stores data as a block data structure, and each block is connected to other blocks by providing cryptographic security and immutability. Link to learning. One of the most popular NoSQL databases is the DBEngine's ranking, which ranks database management systems according to their popularity. The ranking is updated monthly. You can read about the method of calculating the scores. Learning objectives. By the end of this section, you will be able to outline the characteristics of data warehouses, explain the extraction, transformation, and loading ETL process, discuss data marts, describe the technology behind virtual data warehouses and data marts, summarize the nature of operational data stores, identify data lakes and their functionality, compare business intelligence and related tools. With the proliferation of data, new techniques that store and handle the data are required. Data warehousing and data lakes are used for storing big data. Business intelligence analyzes gathered data in data warehouses and data lakes to improve strategic decision-making. Data warehouse characteristics. In the late 1980s, the concept of data warehouse started at IBM when researchers Barry Devlin and Paul Murphy developed the first business warehouse. A data warehouse centralizes an enterprise's data from its databases. It supports the flow of data from operational systems to analytics decision systems by creating a single repository of data from various sources, both internal and external. In most cases, a data warehouse is a relational database that stores processed data that are optimized for gathering business insights. It collects data with predetermined structures and schema coming from transactional systems and business applications, and the data are typically used for operational reporting and analysis. A data warehouse is a collection of data designed to support management's decision-making process and is meant to be subject-oriented. Data are organized based on subjects such as products. Integrated. It integrates data from multiple resources and different formats. Time variant. It stores a time series of periodic snapshots to always be up to date, non-volatile. Data are read only to complete the process of updating or removing data. Data warehouse supports the types of decision-making at the operational, tactical, and strategic levels. Operational decisions happen frequently based on day-to-day operations and are structured based on a specific predefined role, i.e., limited. Tactical level decisions occur with greater frequency, i.e., monthly, and are semi-structured based on the data requirement. The strategic level has the highest level of organizational business decisions, and their decisions are unstructured and/or infrequent. In designing a data warehouse, many schemas can be adopted such as star schema, snowflake schema, and fact constellation. A star schema is a data model with one large fact table connected to smaller tables. The fact table contains keys referring to each dimension table as shown in Figure 8. 19. Illustration of a star schema with fact table, dep key, PR key, student key, connected to department table, dep key, dname, decode, program table, PR key, pname, pcode, and student table, student key, snumber, sname, dob. Figure 8.19. A graphic shows an example of a star schema. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. The snowflake schema is a data model that normalizes the dimension table, Figure 8. 20. It has one fact table, and it creates smaller tables with primary, foreign key relationships. A fact constellation has more than one fact table connected to other smaller dimension tables. Illustration of snowflake schema, connecting sales dimension with customer dimension, name subdimension, time dimension, month subdimension, product dimension, SKU subdimension, category subdimension, company dimension, department list subdimension, region list subdimension. Figure 8.20. This graphic is an example of a snowflake schema. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Extraction, transformation, and loading process. After designing the schema, the next process to start is extraction, transformation, and loading, ETL, which is data integration that combines data from multiple sources, fixes the data format, and loads the data into a data warehouse. The first step is extracting the data from the system, which can be full or incremental extraction. Extraction uses change data capture, CDC, which is a technology that detects any data update event. The second step is transforming the data, which includes formatting the data to be consistent, cleansing the data to get rid of missing data, aggregating data by merging some attributes, and enriching by adding external data. The last step is loading the data in parallel as fact and dimension tables to the data warehouse as shown in Figure 8.21. ETL steps will make changes to the data, which should be documented for better understanding and future maintenance. The documentation includes structural metadata about the data structure and semantic metadata about the meaning. Illustration of RDBMS, external data, codicil, and email going through ETL process, then to staging area, then through an ETL process, ending at a data warehouse. Figure 8.21. The extraction, transformation, and loading, ETL, steps of data are shown as the data makes its way to the data warehouse. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Data mart. A data mart is a scaled-down version of a data warehouse aimed at meeting the information needs of a homogeneous small group of end users, such as a department or business unit. It provides focused content and improves query performance. Dependent data marts pull their data directly from a central data warehouse. Independent data marts are standalone systems drawing data directly from the operational systems, external sources, or a combination of both. Global issues in technology. Storing data. For the past decade, the trend has been to store data in any shape or form without knowing whether it will be used in the future. This has been facilitated by the advent of cloud technology that has allowed people to store unlimited amounts of data at low cost into data lakes. The amount of data stored will keep increasing over the next few decades as daily usage of computer processes keeps increasing. What are some of the global issues you foresee with today's ability to store an unlimited amount of data that may be analyzed at a later time? Virtual data warehouses and virtual data marts. A virtual data mart has no physical data, but provides a single point of access to a set of underlying physical data stores. Data are only accessed, pulled, at query time. A virtual data warehouse can be built as a set of SQL views directly on the underlying operational data sources as an extra layer on top of a collection of physical independent data marts. The metadata model contains the schema mappings between the schemas of the underlying data stores and the schema of the virtual data warehouse, involves query reformulation. A virtual data mart is usually defined as a single SQL view. There can be virtual independent versus virtual dependent data marts. Disadvantages are the extra processing capacity from the underlying operational data sources and the fact that it is not possible to keep track of historical data. Operational data stores. An operational data store, ODS, is a staging area that provides query facilities. It is good for analysis tools that need data that are closer to real time. More complex analyses are still conducted on the actual data warehouse, data lakes. A data lake stores all of an enterprise's structured and unstructured data at any scale. Data lakes are large data repositories that store raw data and can be set up without having to first define the data structure and schema. They allow users to run analytics without having to move the data to a separate analytics system, enabling businesses to gain insights from new sources of data not available for analysis before. For example, by building machine learning models using data from log files, e.g., log files generated by an application that writes to operating system event, clickstreams, e.g. Information about visited pages on the web, social media, e.g., LinkedIn, and IoT devices, e.g., smartwatch. By making all of the enterprise data readily available for analysis, computer data scientists can answer a new set of business questions or tackle old questions with new data. Figure 8.22 shows an example of a data lake process. Illustration of type of data, structured and semi and unstructured, loading to a raw data lake where data is cleaned, standardized, and aggregated to a refined data lake. Figure 8.22, a data lake stores structured, semi-structured, and unstructured data. The store process stores the data as raw data lake, then applies many processes such as cleansing and aggregation to load the data as a refined data lake. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Data warehouses versus data lakes. A data lake is an architectural approach specifically designed to handle data of every variety, ingestion velocity, and storage volume. A data lake allows the storage of massive amounts of data into a central location, so it's readily available to be categorized, processed, analyzed, and consumed by diverse groups within an organization. Because data can be stored as is, there is no need to convert it to a predefined schema as typically required in traditional RDBMS-driven architectures. Consumer usage patterns and the sourcing of the data itself directly influence how data are collected, stored, processed, moved, transformed, automated, and visualized. Data are the ultimate asset with boundless usage patterns now being generated and consumed by humans, machines, devices, sensors, and applications. There are some differences between data warehouse and data lakes listed in Table 8. 11. Characteristic data warehouse, data lake. Data relational, non-relational, and relational. Schema on right. Designed before the implementation, schema on right. Written at the time of analysis. Storage expensive, low cost. Performance fastest query results getting faster. Users decision makers, data scientist. Analysis batch reporting. Business intelligence and visualization machine learning, predictive analysis. Table 8. 11 difference between a data warehouse and a data lake. Data lake development. A traditional approach to information management is no longer suitable due to cost and the inability to adapt. 70% of development costs from ETL include an effort to consolidate, prepare, standardize, and transform data for downstream analytics. Costs involve initial capital investment for hardware, software licensing for databases, data integration, and analytics platforms. There is a need to react to emerging changes in the proliferation of data, new and emerging technologies, and cloud-based integrated service platforms. Traditional data storage and analytic tools can no longer provide the agility and flexibility required to deliver relevant business insights and competitive advantage. Figure 8.23 shows the timeline of a data lake. Timeline: 1990s, EDW Data Cube, 2000s ETL, Datamart/EDW/Cubes. Mid-2000s ETL, Hadoop Data Lake, ending 2000s 10% of data, Cloud EDW, now 75% of databases in the cloud by 2022, Cloud EDW Lakehouse Data Lake Mesh. Figure 8.23, an illustration of a data lake, shows its evolution from an on-premises tool to a cloud version to a hybrid model. Attribution: copyright Rice University, OpenStax, under CC by 4. 0 license. From data lakes to data swamps. A common challenge with the data lake architecture is that without the appropriate data quality and governance framework in place, when terabytes of structured and unstructured data flow into the data lakes, it often becomes extremely difficult to sort through their content. Data lakes can turn into data swamps as the stored data become too messy to be usable. A data swamp is data stored without organization to make retrieval easy. Many organizations are now calling for more data governance and metadata management practices to prevent data swamps from forming. Link to learning. Data lakes are used to collect very large amounts of both relational and non-relational data, such as a streaming service collecting data on users' watching habits, while data warehousing collects relational data, such as when a retailer collects data to use to analyze shoppers' habits and to control inventory. Where does business intelligence fit into this data system? Business intelligence analyzes this data to help in making decisions. They use data for marketing and targeted sales in particular. It can be confusing to understand the ins and outs of each process and how they relate to each other. A blog post about the difference between data lakes, data warehouses, and databases does a great job of distinguishing each and how each contributes to the use of understanding data. Business intelligence. The main goal of the data warehouse is to support decision-making. In order to do that, we need intelligent tools. The set of activities, techniques, and tools aimed at understanding patterns in past data to predict the future is called business intelligence, BI. Modern BI is facilitated through Tableau, ClickView, and Microsoft Power BI. The quality of data controls the quality of results, which means that bad data gives bad insights. Remember GIGO. BI techniques include query and reporting, which provide a graphical user interface, GUI, in which the user can graphically design a report and pivot table, which is a data summarization tool. In addition, one of the BI tools is online analytical processing, OLAP. OLAP is a computer-based approach to analyzing data that enables users to extract and view data from multiple dimensions. It is used to analyze large volumes of data and is commonly used in BI applications. OLAP allows users to perform complex analysis of data by providing a multidimensional view of the data. It can aggregate data across multiple dimensions, such as time, location, product, and customer, enabling users to see trends and relationships that might be hidden in a traditional two-dimensional view of the data. Learning objectives. By the end of this section, you will be able to define big data and explain its related functionality, discuss big data analytics and its impact on computer systems, identify and describe the tools that are used to perform shallow machine learning, describe cognitive analytics and artificial intelligence, identify the tools that are used to perform deep learning, explain massively parallel processing, MPP, database management systems. In the last few years, the amount of data has increased exponentially in many businesses to be big data. Storing, analyzing, and retrieving data has become complex and challenging. Traditional databases and storage cannot deal with big data, which creates new software and hardware business opportunities. Data integration aims to provide a unified view and/or unified access over heterogeneous and possibly distributed data sources. Process integration deals with the sequencing of tasks in a business process, but also governs data flows in these processes. Both data and processes are considered in data integration. The emergence of BI and analytics triggered the need to consolidate data into a data warehouse, big data. The term big data has been in use since the early 1990s, and the term was credited to computer scientist John R. Massey, who is considered the father of big data. Big data is a high volume of data in the shape of structure, semi-structured, or unstructured data. Every minute, more than 300,000 tweets are created. Netflix subscribers stream more than 70,000 hours of video at once. Apple users download 30,000 apps, and Instagram users like almost 2 million photos. In this section, we study the 5 V's of big data examples, new sources of data, data and process integration, data quality and data governance, as well as the privacy, security, and ethical use of data. The 5 V's of big data. Big data helps the decision makers to improve their decisions, which in turn improves the quality of their products and services. Big data has many characteristics. Researchers define the scope of big data as 5 V's, figure 824. Volume, the amount of data, also referred to as data at rest. Velocity, the speed at which data comes in and goes out. Data in motion. Variety, the range of data types and sources that are used, data in its many forms. Veracity, the uncertainty of the data, data in doubt. Value, the actual value derived using the total cost of ownership, TCO, and return on investment, ROI, of the data. 5 V's of big data. Velocity, batch, real-time, processes, streams. Value, statistical, events, correlations, hypothetical. Veracity, authenticity, origin, availability, accountability. Variety, structured, unstructured, multifactor. Volume, terabytes, records, arch, transactions, tables. Figure 824, the 5 V's of big data are volume, velocity, variety, veracity, and value. Attribution, copyright Rice University, OpenStax under CC by 4. 0 license. New sources of data. IoT sources become more numerous and diverse every day. Other sources of data are network data, publicly available data, macroeconomic data, textual data, audio, images, videos, fingerprint, location, GPS, geospatial, RFID data, and many more. We will cover the IoT in more details in Chapter 13, Hybrid Multi-Cloud Digital Solutions Development, Data and Process Integration. Traditionally, a business has various departments that have independent data and systems, i.e. silo from each other. Departments such as human resources and accounting did not integrate and do not share available resources, which makes it hard to answer queries or check updates. To start the convergence of analytical and operational data requires data integration, which provides a consistent view of all organization data. There are different data integration patterns, such as data consolidation, data federation, and data propagation. The use of ETL to capture data from multiple sources and integrate it into a single store, such as a data warehouse, is data consolidation. The use of enterprise information integration, EII, to provide a unified view over data sources is data federation. The use of enterprise application integration, EAI, corresponding to the synchronous or asynchronous propagation of updates in a source system to a target system, is data propagation. A more recent approach to data integration is data virtualization, which is a technique that hides the physical location of data and uses data integration patterns to produce a unified data view. The aim is not only to integrate the data, but also to integrate the process. Process integration aims to integrate the procedures within the business process to improve performance. The main challenge of combining traditional data types with new data types is integrating the diverse data types in such a way that they can be processed and analyzed efficiently. Data quality and master data management. Data quality involves various criteria to assess the quality of a dataset. We need to guarantee a high-quality level to achieve accurate results, GIGO. A data quality dimension includes accuracy, completeness, consistency, and accessibility. The causes of data quality issues are often deeply rooted within core organizational processes and culture. Data preprocessing activities are corrective measures for dealing with data quality issues. Transparent and well-defined collaboration between data stewards and data owners is key to sustainably improving data quality. Data integration can both improve and hamper data quality, e.g., environments where different integration approaches have been combined, leading to a jungle of systems. The series of processes, policies, standards, and tools to help organizations define and provide a single point of reference for all data that are mastered is Master Data Management, MDM. Setting up an MDM initiative involves many steps and tools, including data source identification, mapping out the system's architecture, constructing data transformation, cleansing and normalization rules, providing data storage capabilities, monitoring, and governance facilities. MDM is the generic term of Enterprise Data Management, EDM. EDM is a data management platform for validating the customer data. It is mainly associated with securities data. Data governance. Organizations are increasingly implementing company-wide data governance initiatives to govern and oversee data quality and data integration. In data governance, an organization aims to set up a company-wide controlled and supported approach toward data quality that is accompanied by data quality management processes, i.e., managing data as an asset rather than a liability. Different frameworks and standards have been introduced for data governance. A well-articulated data governance program is a good starting point. Approaches include centralized, i.e., Central Department of Data Scientists handling all analytics requests, decentralized, i.e., all data scientists are directly assigned to business units, and mixed, i.e., centrally coordinated center of analytical excellence with analytics organized at the business unit level. Businesses should aim for top-down, data-driven culture to catalyze trickle-down effects. The board of directors and senior management should be actively involved in analytical model building, implementation, and monitoring processes. Data governance has different standards such as Total Data Quality Management, TDQM, Capability Maturity Model Integration, CMMI, Data Management Body of Knowledge, DMBOK, Control Objectives for Information and Related Technology, COBIT, and Information Technology Infrastructure Library, ITIL. TDQM is a model that defines, measures, and improves the quality of the data in the organization. CMMI is a model that helps organizations to improve the reliability by decreasing risks in services and products by developing the system behaviors. DMBOK is a collection of best practices for each data management process, such as data modeling, data quality, documentation, data security, and metadata. COBIT is a framework that helps organizations that are looking to improve and monitor their data management system. ITIL is a framework that improves efficiency to achieve the predictable services using standardized design. Privacy and security of data. The concept of data security pertains to the following concerns: guaranteeing data integrity and data availability, i.e., ensuring that data are accurate and available when needed, authentication, i.e., verifying the identity of a user, access control, i.e., controlling who has access to data and what actions they can perform, guaranteeing confidentiality, i.e., ensuring that data are kept confidential and are not disclosed to unauthorized users, auditing, i.e., tracking all access and activity related to data, and vulnerabilities, i.e., identifying vulnerabilities in systems and data. To better understand privacy, we should start with the RACI, responsible, accountable, consulted, and informed. Responsible defines who is responsible for developing the data. Accountable defines the people who decide what should be done with the data. Consulted defines domain expertise to advise the data scientist. Informed defines a set of people who should be up to date on the working process. To access internal data, a data scientist should file a data access request to specify the target data and the length of time needed for access. There are many available privacy regulations, such as the General Data Protection Regulation, GDPR, Privacy Act of 1974, Health Insurance Portability and Accountability Act, HIPAA of 1996, the Electronic Communications Privacy Act, ECPA of 1986, and the Privacy Shield. The Privacy Shield is a framework for exchanges of personal data between the European Union and the United States. Big data analytics. While storage and computing needs have grown by leaps and bounds in the last several decades, traditional hardware has not advanced enough to keep up. Enterprise data no longer fits neatly into standard storage, and the computational power required to handle most big data analytics tasks may take weeks or months, or may be impossible to complete. To overcome this deficiency, many new technologies have evolved to include multiple computers working together, distributing the database to thousands of commodity servers. When a network of computers is connected and works together to accomplish the same task, the computers form a cluster. A cluster can be thought of as a single computer, but can dramatically improve the performance, availability, and scalability over a single, more powerful machine at a lower cost by using commodity hardware. Concepts in practice. Private data and analytics. All social media and search engine websites use data management for machine and deep learning applications. Today, there are major concerns related to the use of private data to perform analytics and support targeted sales or broadcast fake news to select customers. Being able to control the use of private data is essential so it does not get manipulated and end up being misused for various reasons. Data compliance is attempting to address this very problem, and various regulations have already been put in place in the United Kingdom and Europe via the GDPR regulations. The same is happening in the United States, with regulations being put in place in some states, including California in particular. Analytics process model. An analytics process model provides a statistical analysis using a set of processes to solve system problems and find a new market opportunity. There are many sample applications for analyzing data such as risk analytics, e.g., credit scoring, fraud detection, marketing analytics, i.e., using data to evaluate the success of marketing strategies, response modeling, i.e., statistical platform to model the relationship between the customer's responses and the predicted values, customer segmentation, i.e., dividing the customers into groups with each group sharing the same characteristics to improve the marketing strategy, recommender systems, i.e., a filtering system that provides suggestions for products based on customer rating, and text analytics, i.e., identifying a pattern to understand the data. Creating a viable data management infrastructure for analytics applications involves much more than just building a simple machine learning model. It requires an understanding of how all the parts of the enterprise's ecosystem work together, where how the data flows into the data team, the environment where the data are processed transformed, the enterprise's conventions for visualizing presenting data, and how the model output will be converted as input for some other enterprise applications. The main goal is to build a process that is easy to maintain and where models are iterated on, the performance is reproducible, and a model's output can be easily understood and visualized for other stakeholders so that they may make informed business decisions. Achieving those goals requires selecting the right tools as well as an understanding of what others in the industry are doing along with best practices. Figure 8.25 shows the three-stage process of the analytics process model, which we discuss next. Illustration of analytics process model. Preprocessing, identify problem, identify data sources, select, clean, transform. Analytics, analyze. Post-processing, evaluate and deploy. Figure 8.25. The three stages of the analytics process model are shown. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Data preprocessing. To preprocess the data, a data scientist may use denormalizing, the merging process, sampling, exploratory analysis, missing values, and outlier detection and handling. The process of merging several normalized data tables into an aggregated, denormalized data table is called denormalizing. The merging process involves selecting information from different tables about a specific entity and then copying it to an aggregated table. Selecting a subset of historical data to build an analytical model is called sampling. The process of summarizing and visualizing data for initial insight is called exploratory analysis. Filling the empty field or deleting it involves resolving a missing value. An outlier is a value outside the population that should be detected in order to apply the handling process on it. Types of analytics. After finishing the preprocessing, the analytics step will start. Figure 8.26. This step aims to extract a decision model from the preprocessed data. To build such a model, there are many models, such as predictive analytics, evaluating predictive models, descriptive analytics, and social network analytics. Illustration of data mining, association analysis, apiary/FP growth algorithm, classification, decision tree, Bayesian networks, cluster analysis, K-means hierarchical clustering, and machine learning, supervised unsupervised learning, regression model decision trees, clustering association, other reinforced deep learning. Figure 8.26. Many techniques can be used to analyze data in order to make a business decision. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Predicting the target measure of interest using regression, e.g. linear regression, logistic regression, and classification, e.g. decision trees, is predictive analysis. Evaluating predictive models splits up the dataset with specific performance measures. Patterns of customer behavior, e.g. association rules, sequence rules, and clustering, are considered descriptive analytics. Global issues in technology. Predictive analytics. Predictive analytics is a set of techniques that uses data, statistics, and machine learning to make predictions about future events and/or behaviors. These predictions rely on data being accurate and unbiased to provide value. As we move toward generative artificial intelligence, Gen AI, technology that makes use of existing data to create large language models. Issues associated with the possibility of using biased data to train these models are becoming critical. Recent research is focusing on fairness in the decisions taken by models trained with biased data, and on designing methods to increase the transparency of automated decision-making processes so that possible bias issues may be easily spotted and fixed by removing bias. Post-processing of analytical models. The last step is the post-processing step, and the first activities in this step are interpretation and validation. Business experts validate the data and detect any unknown pattern. In addition, sensitivity analysis takes place in post-processing to verify the robustness of the created model. After that, experts approve the deployment of the model and the production activity can start. Finally, the expert applies the backtesting activity to be sure the model produces the correct output. Evaluating analytics. Analytics models should solve the business problem for which it was developed, business relevance, and should be acceptable statically, statistical performance, and validity. The analytical model should be understandable to the decision maker, interpretability, and operationally efficient. Measuring the model performance uses TCO and ROI. The total cost of ownership, TCO, represents the cost of owning and operating the analytical model over time. The calculation of return on investment, ROI, determines the ratio of net profits divided by the investment of resources. Then get through machine learning. You are given a dataset that pertains to hospital patients affected with a particular condition, and you are asked to create a predictive model that could be used to assess testing new individuals for this condition. Would you use shallow or deep machine learning to solve this problem? Explain your dataset and logic for solving the healthcare problem. Big data analytics frameworks for shallow machine learning. Big data analytics creates a model from a set of data, and to learn from the data, we need machine learning, ML, algorithms. This section discusses MapReduce, Hadoop framework, SQL on Hadoop, Apache Spark framework, streaming big data analytics, on-premises versus cloud solutions, and searching unstructured data and enterprise search. MapReduce. MapReduce is a two-step computational approach for processing large, multi-terabyte or greater, datasets distributed across large clusters of commodity hardware in a reliable, fault-tolerant way, Figure 8. 27. The first step is distributing data across multiple computers, MAP, with each performing a computation on its slice of the data in parallel. The next step combines those results in a pairwise manner, reduce. Illustration of big data input going through MAP, then reduce, resulting in output. Figure 8. 27. After the data input stage, MAP will start then reduce to produce the output. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. Hadoop framework. Hadoop is distributed data infrastructures that leverage clusters to store and process massive amounts of data. An open-source software framework used for distributed storage and processing of big datasets can be set up over a cluster of computers built from normal commodity hardware. Many vendors such as Amazon, Cloudera, Dell, Oracle, and Microsoft offer their implementation of a Hadoop stack. Hadoop leverages distribution and consists of three main components. Hadoop Distributed File System, HDFS, a way to store and keep track of data across multiple, distributed, physical hard drives. MapReduce, a framework for processing data across distributed processors. Yet another resource negotiator, Yarn, a cluster management framework that orchestrates the distribution of CPU usage, memory, and network bandwidth allocation across distributed computers. Hadoop is built for iterative computations. It scans massive amounts of data in a single operation from disk, distributes the processing across multiple nodes, and stores the results back on disk. Hadoop is typically used to generate complex analytics models or high-volume data storage applications, such as retrospective and predictive analytics that involve analyzing past data to identify trends. Machine learning and pattern matching that involve using algorithms to automatically identify patterns and trends in data. Customer segmentation and churn analysis that involve dividing customers into groups based on shared characteristics or behaviors, and using this information to better understand their needs and preferences. And active archives that involve storing data in a way that allows it to be easily accessed and used for analytics purposes. SQL on Hadoop. Because of the complexity of MapReduce in a database query, many industries create other solutions. In 2007, Hadoop included the first version of HBase as a data storage platform. HBase offers a simplified structure and query language for big data. Similar to an RDBMS, HBase organizes data in tables with rows and columns. Yahoo developed Pig, which is a high-level platform for creating programs that run on Hadoop, and its language is Pig Latin, which uses MapReduce underneath. It somewhat resembles the querying facilities of SQL. Facebook developed Hive, which is a data warehouse solution offering SQL querying facilities on top of Hadoop. It converts SQL-like queries to a MapReduce pipeline. It also offers a JDBC and ODBC interface and can run on top of HDFS as well as other file systems. Apache Spark Framework. MapReduce processes data in batches. Therefore, it is not suitable for processing real-time data. Apache Spark is a parallel data processing tool that is optimized for speed and efficiency by processing data in memory. It operates under the same MapReduce principle, but runs much faster by completing most of the computation in memory and only writing to disk when memory is full or the computation is complete. Streaming big data analytics. Data streams come from devices, sensors, websites, social media, and applications. Streaming analytics performs an analytic process on streaming data, which is useful for real-time flow of data. There are many big data streaming analytics platforms such as Amazon Kinesis Data Firehose, which is a streaming data service to capture, process, and store data streams at any scale. The Array of Things (OT) is an open-source network that collects and returns urban data in real time. Azure Stream Analytics is a real-time analytics, event processing engine to analyze big data streaming from multiple sources. On-premises versus cloud solutions. Another innovation that has completely transformed enterprise big data analytics capabilities is the rise of cloud services. Before cloud services were available, businesses had to buy on-premises data storage and analytics solutions from software and hardware vendors, pay upfront for perpetual software license fees and annual hardware maintenance, pay service fees along with the costs of things such as power, cooling, security, disaster protection, and IT staff for building and maintaining the on-premises infrastructure. Even when it was technically possible to store and process big data, most businesses found it cost prohibitive to do so at scale. Scaling with on-premises infrastructure also requires an extensive design and procurement process, which takes a long time to implement and requires substantial upfront capital. Many potentially valuable data collection and analytics possibilities were ignored as a result. Some key benefits of cloud computing include scalability, flexibility, cost savings, reliability, and disaster recovery. Link to learning. Businesses can significantly reduce costs and improve operational efficiencies with cloud services because they can develop and produce their products more quickly with the out-of-the-box cloud resources with built-in scalability. Cloud services remove the upfront costs and time commitment to build on-premises infrastructure. Cloud services also lower the barriers to adopt big data tools, which has the effect of democratizing big data analytics for small and mid-sized businesses. Using cloud services allows startup and small companies to develop and scale solutions quickly, making it possible for them to compete with larger organizations. You can discover how companies and their data scientists use the cloud to deploy data science solutions to production or to expand computing power. Searching unstructured data and enterprise search. Searching for information in documents using retrieval models that specify matching functions and query representation is information retrieval. Enterprises use a variety of retrieval models for intranet, web search, and analysis, such as keyword queries that use a keyword to retrieve documents, Boolean queries that use logical operators to retrieve the documents, phrase queries that perform exact phase retrieval, proximity queries that check how close to each other within a record multiple entities are, wildcard queries that support matching expressions, and natural language queries that try to formulate answers to a specific question from retrieved results. Searching unstructured data is challenging. A full-text search is selecting individual text documents from a collection of documents according to the presence of a single or a combination of search terms in the document. Indexing full-text documents is the process of adding an index for every search term that consists of term and pointer, with each pointer referring to a document that contains the term. Web search engines search a web database and gather information related to a specific term. An enterprise search is the process of making content stemming from the databases by offering tools that can be used within the enterprise. Cognitive analytics and artificial intelligence. The technology that tries to simulate a human's way of solving problems, e.g., Siri and Alexa, is called cognitive computing. Artificial intelligence, AI, is a system that creates intelligent ways to solve problems that previously required human interaction. Cognitive computing. Three components must interact to achieve AI, Figure 8. 28. Syntax structure, semantics meaning, and inference reasoning planning. Human intelligence requires that these three components rely on some form of data management and relate to deep learning of other brain functions, such as restricted Boltzmann machines, stacked autoencoder, and deep belief networks. Restricted Boltzmann machines are artificial networks that can learn a probability distribution using a set of input. Stacked autoencoder is an artificial network used to learn unlabeled data through efficient coding. Deep belief networks are intelligent networks used to invent a solution for a specific problem when the traditional intelligent network could not solve it. Illustration of head with language and vision inside, with semantics, inference, and syntax circling around. Figure 8. 28 components of artificial intelligence include syntax, semantics, and inference. Attribution. Copyright Rice University, OpenStax under CC by 4. 0 license. Sample AI applications. Amazon provides various ML services. They allow developers to integrate cloud ML into mobile and other applications. Amazon Lex allows users to incorporate voice input into applications, extension of Amazon's Echo product, so that users can ask questions about everything from the weather to news and streaming music. Amazon Polly is the opposite of Lex. Polly turns text into speech in 27 languages. Amazon Recognition, which is at the cutting edge of deep learning applications, takes an image as input and returns a textual description of the items that it sees in that image by performing detailed facial analysis and comparisons. Reinforcement and transfer learning. The machine learning method based on encouraging desired behaviors and removing undesired behaviors is called reinforcement. The machine learning method based on reusing the result of a specific task to start a new task is called transfer learning. A deep learning network is a type of machine learning method based on artificial neural networks, Figure 829. Artificial neural networks simulate the network of neurons to make a computer learn and make decisions like the human brain does e.g. recurrent neural networks or RNNs, which are an artificial neural network, uses time series data. There are various classes of deep learning networks such as cloud-based deep learning frameworks such as Microsoft Cognitive Toolkit, which is an open-source toolkit for commercial-grade distributed deep learning. Google TensorFlow system applications for neural network computing and deep learning, such as handwritten digit recognition and cognitive services. Predictive software libraries for cognitive applications, such as Keras, which is an open-source software library that provides a Python interface for artificial neural networks. Illustration of input as purple circle, next to column of green circle, connected by arrows to blue circles. Connected to a peach circle labeled output. Figure 8. 29. The deep learning process uses artificial neural networks. Credit. Modification of neural network by Loxx/Wikimedia Commons, CC0. Cognitive analytics frameworks for deep machine learning. In this section, we introduce examples of cognitive analytics frameworks for deep machine learning applications such as Spark MLib, Amazon Machine Learning Platform, and MXNet, Google TensorFlow, Azure Machine Learning Platform, and Microsoft Cognitive Toolkit. Spark MLib. Spark ML includes a high-level API, Spark Machine Learning Library of MLib for creating ML pipelines. Data can be fed into data frames, and the library enables the quick creation of a machine learning processing pipeline by combining transformers and estimators. MXNet. MXNet is an open-source library for distributed parallel machine learning that was developed at Carnegie Mellon University, the University of Washington, and Stanford University. MXNet can be programmed with Python, Julia, R, Go, MATLAB, or C++, and runs on many different platforms including clusters and GPUs. It is also now the deep learning framework of choice for Amazon. Google TensorFlow. Google's TensorFlow is a frequently discussed and used deep learning toolkit. If you have installed the Amazon Deep Learning AMI, you already have TensorFlow installed, and you can begin experimenting right away. Azure Machine Learning Platform and Microsoft Cognitive Toolkit. The Microsoft Cognitive Toolkit software is available for download in a variety of formats so that deep learning examples can be run on Azure as clusters of Docker containers. Multiple nodes joined using a special configuration. Industry Spotlight. MPP is NYSE VIP. The New York Stock Exchange, NYSE, receives 4 to 5 TB of data daily and conducts complex analytics, market surveillance, capacity planning, and monitoring. It had been using a traditional database that could not handle the workload. It took hours to load and had poor query speed. Moving to an MPP database reduced their daily analysis runtime by 8 hours. Massively parallel processing, MPP, databases. Similar to MapReduce, massively parallel processing, MPP, databases are referred to as NewSQL as opposed to NoSQL. MPP distributes data processing across multiple nodes, and the nodes process the data in parallel for faster speed. Unlike Hadoop, MPP is used in RDBMS and utilizes a share-nothing architecture. Each node processes its own slice of the data using multi-core processors, making them many times faster than traditional RDBMS. Some MPP databases, such as Pivotal Greenplum, have mature machine learning libraries that allow for in-database analytics. In an MPP system, all the nodes are interconnected, and data could be exchanged across the network. However, as with traditional RDBMS, most MPP databases do not support unstructured data, and even structured data will require some processing to fit the MPP infrastructure. Therefore, it takes additional time and resources to set up the data pipeline for an MPP database. Because MPP databases are ACID compliant and deliver much faster speed than traditional RDBMS, they are usually employed in high-end enterprise data warehousing solutions such as Amazon Redshift, which is a data warehouse cloud platform for Amazon Web Services, and Pivotal Greenplum, which is a big data technology based on MPP architecture combined with an open-source database. Learning objectives. By the end of this section, you will be able to define informatics and discuss its applications in various industries. Explain the role and life cycle of information systems. As discussed earlier, the data analysis process produces reports that help the decision maker at all management levels. Informatics is collaborating activities that involve humans and technologies to apply data management tools. Definition and applications. The term informatics broadly describes the study, design, and development of information technology for the good of people, organizations, and society. Informatics focuses on computer systems from a user-centered perspective and studies the structure, behavior, and interactions of natural and artificial systems that store, process, and communicate information. Informatics has applications in many areas including sports informatics, behavior informatics, business informatics, privacy informatics, community informatics, geoinformatics, health informatics, imaging informatics, museum informatics, research informatics, social informatics, and urban informatics. Informatics as a data management solution. Informatics leverages information sciences, big data analytics, electronic records management, digital assets management, and information security and governance, human-computer interaction, human-centered design, information system analysis and design, telecommunications structure, and information architecture and management. All these fields are supporting components of end-to-end data management solutions. Therefore, one can view informatics as a data management solution. Informatics information systems. Information systems support informatics and provide an organizational context for using database systems to help collect, organize, store, analyze, preserve, retrieve, and govern data and records relevant to an organization. These systems also help informatics professionals turn data and information into actionable knowledge from a user-centered perspective within the context of specific disciplines or industry, such as health or sports. Helping uncover critical information that can improve the user experience may ultimately lead to achieving a company's goals and is an example of how valuable informatics is to a business. Think it through. Informatics approach. Suppose you work for a healthcare provider and you have been tasked with developing and launching a new patient portal to help patients better communicate with healthcare providers while providing patients easy access to their healthcare data. What will your technical requirements be in relation to software, hardware, data, and network? What will you need to support an informatics solution? What approach will you take? Information system creation life cycle. Information systems provide resources involved in the collection, management, use, and dissemination of information resources of organizations. The macro life cycle for the creation of an information system includes feasibility analysis, requirements collection and analysis, design, implementation, and validation and acceptance testing. The micro life cycle for the creation of an information system focuses on system definition, database design, database implementation, loading or data conversion, application conversion, testing and validation, operation, monitoring, and maintenance.